Okay, ready to dive into this. It's testing approximate stationarity concepts for piecewise affine functions.
Really interesting stuff.
Yeah, and clearly, you're into some pretty advanced math, so
Oh, absolutely.
we're gonna go deep here. We're talking computational complexity of finding those stationary points, and then
Yeah.
Frechet and Clark subdifferentials, even that
Yeah.
connection between geometry and non-smooth analysis.
It's fascinating how this paper really tackles this fundamental issue, right? How do we efficiently locate those points, those stationary points on a
Yeah.
function? And then especially when we're talking about piecewise affine functions, it gets even trickier.
Absolutely.
Yeah.
So, to ground ourselves, maybe just a super quick recap of what makes those PA functions so unique.
Sure. So imagine you have like a landscape and it's made up of all these different flat planes that are just kind of joined together. Each of the planes is like a simple linear equation. But where they intersect, you get these like, sharp edges or kinks. An example is the absolute value function. You have like two linear pieces and
Mhm.
then they meet at that sharp point at 0.
Gotcha. Okay, so the paper jumps right into this subgradient method and its limitations with these PA functions, and specifically fact 1.1 um, highlights this sort of asymptotic nature of its convergence. Can you maybe expand on that a little bit?
Sure. So fact 1.1 is basically telling us that if we apply the subgradient method to a PA function and certain conditions are met, we will eventually get arbitrarily close to a stationary point.
Okay.
However, the convergence is asymptotic, and it doesn't actually give us like a clear timeline.
So it's kind of like saying, keep heading west and you'll eventually hit the coast, but we're not saying how many miles or how many days it'll take.
Yeah, exactly. Exactly.
Hmm.
And then fact 1.2 actually just drives this point home further, right? It says that there's actually no way to guarantee that the subgradient method will find like an approximate stationary point within a predetermined number of steps.
Okay, so how do we escape this endless optimization hike? The paper mentions this idea of shifting our focus to a posteriori analysis. What is that all about?
So instead of trying to predict beforehand, like how long it's going to take to find this approximate stationary point,
Right.
we kind of look at it after we run the subgradient method for a while and say, okay,
Okay.
given where we are now, how can we determine if we're close enough to a stationary point?
And this is where that concept of near-approximate stationarity or NAS comes in.
Exactly. So it's basically a way to define how close we are to an actual stationary point. So
Okay.
picture like a small ball around our current point, and it has a radius of time.
Okay.
So INAS basically means that within this ball, we can find a point where a subgradient exists that has length less than or equal to.
So instead of searching for a perfectly level surface, we're
Right.
kind of accepting that there might be some bumps, but as long as it's within a certain tolerance, we're good.
Exactly. Exactly.
Makes sense.
Yeah.
But how do we even begin to find these mass points? Because the paper's throwing around terms like NP hard and co-NP hard, which,
Right.
sound computationally pretty daunting.
Yeah. So these are basically complexity classifications, and they highlight some of the challenges that we're facing. So, NP hard problems are at least as hard as the toughest problems in the class NP.
Okay.
And so essentially what this means is you can verify a solution very quickly if someone gives you one.
Yeah.
But finding it in the first place could take like, eons. And then co and p hard problems are very similar, but they deal with the difficulty of disproving something.
Okay.
So when the paper's labeling certain stationarity tests as NP hard or co-NP hard, it's really underscoring that it could be a computational nightmare.
So even verifying if we've kind of stumbled upon the right answer could be a problem in itself. It's kind of a grim picture that's being painted here. Does the paper offer any solutions, or are we just stuck with these computational roadblocks?
So the paper does provide some clever workarounds. One really interesting idea is connected to the subdifferential sum rule,
Okay.
which is a concept that comes from convex analysis.
Yeah.
And this rule works beautifully when you're dealing with convex functions.
Yeah.
But applying it to non-convex functions, especially like our PA friends, can get very messy.
Yeah. Yeah. I remember that subdifferential sum rule from my calculus days.
Yeah.
But how can we apply that to a non-convex PA function without just, causing chaos?
That's a great question. That's precisely what the paper explores. So they delve into the conditions where this rule can actually be applied to non-convex PA functions without losing, vital information.
Right.
And they introduce this really interesting concept called compatibility.
Okay.
For polytopes, which are these multidimensional shapes with flat sides.
We're talking like cubes and pyramids, things like that.
Exactly. And they use compatibility to characterize when the subdifferential sum rule holds exact for PA functions. So it's linking the geometry of these polytopes to the properties of the subdifferential sum rule.
So the shape of these objects dictates how we analyze the function's behavior.
Yeah.
But how does compatibility actually help us find those approximate stationary points?
So what this does is it actually allows us to check the accuracy of a simpler approach.
Okay.
That's called the subdifferential relaxation and reduction method, or SRR. So imagine you're replacing a really complicated lock with a simply one that's easier to pick, right?
Okay.
That's kind of what SRR does.
Okay.
And so if those polytopes we were talking about, if they are compatible, then this relaxed approach will actually give us the correct answer.
So compatibility acts as like kind of a guarantee that our simplified method is still on the right track. But how do we even determine if these polytopes are compatible in the first place? Sounds computationally pretty intense.
Yeah, you're right. So directly checking for compatibility can still be very computationally expensive. So they introduce another concept called transversality.
Okay.
Which is actually a polynomial-time verifiable condition. So think about, two lines intersecting at a clean angle. That's transversal, right?
Okay.
So they apply this concept to the subspaces that are associated with these polytopes.
Okay.
Essentially checking if these multidimensional shapes are kind of intersecting in a well-behaved way.
Okay, I'm getting a sense of the geometry at play here. But how does transversality actually relate to compatibility?
So they prove that if two piecewise affine functions are transversal at a point, then those polytopes, they're guaranteed to be compatible. So it's like saying if these shapes intersect neatly, then we can safely use that simpler SRR method.
Gotcha. So transversality is kind of our shortcut to verify these conditions for this SRR method, and it's computationally manageable. That's great.
Yeah.
But how does all of this tie back to finding those NAS points we were talking about before?
So that is where the paper takes a really interesting turn. They introduce a new algorithm called the butterfly net algorithm.
Now we're talking. Tell me about this butterfly net.
So it's a very geometric approach. Imagine you're trying to find something in a very large field.
Okay.
And so what the butterfly net algorithm does is it divides the space around our current point into smaller sections.
Okay.
And then it systematically searches each section for a near-approximate stationary point.
So a much more organized, systematic approach compared to just randomly kind of wandering around, hoping to stumble upon a solution. What's the butterfly part of this analogy?
The paper doesn't really explain why it's called that, but my guess is it has something to do with how the algorithm is subdividing the space, right? It's like the wings of a butterfly, spreading out and covering these different areas.
Okay, I like that.
In a structured way.
Yeah, it's a nice poetic way of visualizing this algorithm.
Yeah.
What does this butterfly net algorithm ultimately achieve?
So it either confirms that our current point is indeed a near-approximate stationary point, meaning we're close enough to that flat spot.
Yeah.
Or it tells us to keep searching elsewhere. So it's like having a compass. That's guiding us towards these desirable points.
Great. And it does this in a finite number of steps.
Exactly.
So no more endless wandering.
No more endless wandering.
Okay, good.
And the algorithm.
But we established before that testing for that exact stationarity can be incredibly difficult. So how do we use this exact astationarity testing oracle in this algorithm?
That's a great question. And the paper actually presents a very interesting paradox.
Ooh, a paradox.
Love it. They demonstrate that if we only have local information about the function, meaning we can only see a small neighborhood around our current point.
Right.
No algorithm can guarantee finding a near approximate stationary point within a reasonable time frame.
So even with this powerful butterfly net algorithm, we're kind of limited by the amount of information that's available to us.
Exactly. It's like navigating a maze,
Yeah.
but you can only see a few steps ahead.
Right. Yeah.
However, the butterfly net still proves very valuable in practical settings where we have access to more than just this local information. So it's like having a map to guide us.
Gotcha.
Even if we can't just teleport to our destination.
Okay, that clarifies things.
Yeah.
Now, the paper mentions some applications of this work to these specific machine learning problems.
Right.
Like SVMs with margin loss and continuous piecewise affine regression. Can you elaborate on that a little bit?
Sure. So they demonstrate how these insights that we've kind of gleaned about PA functions actually apply to problems like support vector machines
Okay.
with margin loss and continuous piecewise affine regression.
Let's unpack that a little bit, starting with SVMs. What is this margin loss all about?
So in essence, it's basically enhancing the robustness of SVMs against outliers.
Okay.
So those data points that
Yeah.
don't really fit the pattern. So imagine you're trying to, draw a line separating two groups of points.
Yeah.
The standard SVM loss function can actually be heavily influenced by these outliers.
Right.
So margin loss basically ignores those outliers that are too far away, so the line's less sensitive to their influence.
So it's kind of a way to prevent a few rogue data points
Yeah,
from
thanks.
hijacking our decision boundary.
Exactly.
Interesting. And so the paper applies these concepts that we've been talking about, like transversality and the subdifferential sum rule, to analyze this particular SVM problem.
Exactly. So we're not just dealing with this abstract math, right? We're using these concepts to actually improve
Right.
machine learning algorithms.
That's impressive. And what about continuous piecewise affine regression? How does that connect to our discussion?
So instead of fitting like a straight line to our data,
Right.
we're now aiming to fit a piecewise affine function.
Okay.
And this allows our model a little more flexibility to capture nonlinear relationships.
Okay, so we're moving beyond linear models.
Exactly.
Gotcha. How does the paper link this to the concepts that we've been exploring?
So they actually demonstrate how to transform the continuous piecewise affine regression problem into a form where we can apply the tools we've developed for analyzing PA functions.
Okay.
So this allows us to study the stationarity properties of this more complex.
Wow, fascinating. So we've gone from kind of exploring this very abstract realm of PA functions to seeing how these concepts have very, very tangible applications
Yeah.
in machine learning. This has been an incredibly mind-bending deep dive.
Right.
I feel like we've uncovered this kind of hidden world within optimization. Maybe we should pause here for now and continue our exploration in the next part.
Yeah, sounds good.
Okay, great. Until next time, happy optimizing.
Happy optimizing. Back again, continuing our deep dive into these fascinating piecewise affine functions.
Yeah, it's like we've stumbled into this hidden valley
Right.
and this vast landscape of optimization.
Right.
We're ready to explore
Yeah.
all the intricate paths.
Do it.
But before we venture too far, I'd love to dig a little deeper into those computational challenges we touched on earlier. The paper presented some, fairly daunting results
Right.
about the complexity of testing for stationarity
Right.
in PA functions.
Yeah.
Can you remind us why this is such a tricky business?
Sure. So it really boils down to this complex interplay
Okay.
between the different components of a PA function and their subdifferentials.
Yeah.
So you can imagine like a function that's defined as the difference of two convex piecewise affine functions.
Okay.
And to find a stationary point, we essentially need to analyze how these two components interact,
Okay.
particularly their subdifferentials.
You've mentioned subdifferentials a couple of times now, and it's been a while since my last calculus deep dive. Can we just quickly recap what those represent?
Of course. So think of a subdifferential as a set that captures all possible slopes of a function
Okay.
at a specific point. So for smooth functions,
Yeah.
the subdifferential is very simple. It only contains the gradient, which is just a single vector
Yeah.
pointing in the direction of steepest descent. But for non-smooth functions, like PA functions, things get a little bit more interesting. So, we've talked about those kinks in corners before. And what that means is there could be multiple slopes at a point.
Okay.
And so that results in a set of subgradients.
So the subdifferential kind of captures all those possible directions the function could be moving at a non-smooth point.
Exactly.
And ultimately, we're looking for those points where the subdifferential contains the zero vector,
Right.
meaning that it's essentially flat. at that location.
Exactly. Now, for convex functions, we have this handy tool called the subdifferential sum rule.
Okay.
And what this rule states is that the subdifferential of the sum of two convex functions is simply the sum of their individual subdifferentials.
Okay.
Very straightforward.
That sounds very convenient. What's the catch? Why doesn't this lovely rule just solve all our problems?
So the catch is that this rule doesn't always hold true for non-convex functions,
Right.
like our PA functions. And determining whether or not a point satisfies the exact stationarity condition, meaning checking if the subdifferential of the difference of these two convex PA functions contains the zero vector, can actually be computationally as hard as some notoriously difficult problems in computer science.
So even with a seemingly simple rule,
Right.
things can really spiral into complexity when we're dealing with non-convex functions.
Exactly.
The paper highlighted this difficulty with a series of hardness results.
Yes, exactly. So it demonstrates that testing for various stationarity concepts, including fresh stationarity, Clark stationarity, and even like a weaker notion called DC criticality, can be computationally intractable in general.
Let's unpack those stationarity concepts a little bit.
Right.
What distinguishes Frechet stationarity from Clark stationarity?
Sure. So they offer two different perspectives on what it means for a function to be stationary at a non-smooth point.
Okay.
So fresh stationarity is like the stricter condition, right?
Yeah.
So it demands that the function be flat in all directions.
Right.
Clark stationarity is a bit more relaxed.
Okay.
So it only requires that the function be flat along a specific set of directions.
So fresh stationarity is like searching for a perfectly level surface, while Clark stationarity allows for some minor bumps and dips.
Exactly.
Okay.
And so the paper demonstrates that testing for either of these conditions can be computationally challenging.
For PA functions.
Right.
And what about DC criticality? You mentioned it was even weaker than Clark stationarity.
Right. So DC criticality applies specifically to functions that can be represented as the difference of two convex functions.
Okay.
Hence the DC, right?
Okay.
And essentially what it does is it checks whether or not the subdifferentials of these two convex components share at least one slope in common.
So even with this more relaxed condition, we're still not out of the computational woods.
Unfortunately not. The paper shows that testing for DC criticality in PA functions is still NP hard.
Okay.
And so these hardness results, they really highlight the inherent difficulty of pinning down those stationary points for PA functions.
Right.
Which has, puzzled researchers for quite some time.
Yeah, this all sounds a bit disheartening. Are we doomed to just wander aimlessly in this computational wilderness forever? Does the paper offer any hope for finding solutions?
Certainly. So while the paper does a fantastic job of exposing the challenges, it also presents some really ingenious solutions.
Okay, good.
And one key insight is to actually focus on a particular representation of PA functions called the max-min form.
The max-min form, another new term to add to our optimization lexicon. Can you enlighten us?
So in the max-min form, a PA function is expressed as the maximum of a finite number of functions, each of which is the minimum of a finite number of affine functions.
Okay.
So it's like constructing this complex structure by carefully assembling simpler building blocks.
Okay, I'm starting to visualize this. How does this max-min form help us overcome those computational roadblocks we were discussing?
So the beauty of this max-min form lies in its ability to actually streamline the calculation of the subdifferential.
Okay.
So remember how we discussed that computing the subdifferential for a general PA function could be a nightmare?
Right.
Well, the max-min form provides a much more manageable blueprint for piecing together those subdifferential components.
So it's like having a more organized map.
Exactly.
To navigate that complex terrain.
Right.
And this leads to more efficient stationarity testing.
Exactly. It's like finding a hidden shortcut through that computational maze.
That's a welcome relief. It seems like this max-min form offers a glimmer of hope in this challenging landscape.
Yeah.
The paper also explored the conditions under which that helpful subdifferential sum rule actually applies to PA functions in the max-min form.
Right. Exactly.
And to characterize when this rule holds true,
Yeah.
they introduced this concept of transversality.
Wait, didn't we
didn't we encounter transversality?
You do.
When we were talking about those compatible polytopes? Are we dealing with the same concept here?
You have a keen eye. We are indeed using the same term.
Okay.
But it has a slightly nuanced meaning in this context.
Okay.
So it's still a geometric concept.
Yeah.
But now it focuses on how those subdifferential sets intersect.
So the same term can have subtly different
Right.
interpretations depending on
It can.
the specific mathematical context.
It can.
Context is king, as they say.
Precisely. And in this case, transversality unlocks the power of the subdifferential sum rule for PA functions in the max-min form.
Okay, so we have the max-min form and transversality
Right.
as our allies.
Our allies.
in this computational battle. What other tricks does the paper have up its sleeve?
So they introduce a really clever algorithm
Okay.
called the butterfly net algorithm.
Hold on. The butterfly net algorithm. Isn't that the same algorithm that we explored in the context of just, general
It is a
PA functions?
It is. It's the same algorithm, but now we're applying it to PA functions that are represented in the max-min form.
So we're repurposing our trusty butterfly net
Exactly.
in a slightly different setting.
Right.
Gotcha.
Exactly.
Right.
And it proves to be equally effective in this context. So the butterfly net algorithm very cleverly leverages the structure of the max-min form
Yeah.
to hunt down those near-approximate stationary points.
Can we revisit how this algorithm operates? I recall it being a little mind-bending, even with that helpful butterfly analogy.
Yeah. So imagine you have this finely woven net.
Okay.
And you're tasked with catching butterflies in this vast field.
Yeah.
And so instead of swinging your net around randomly, you strategically position it in areas where butterflies are most likely to flit about.
Right.
Right. And so that's essentially what the butterfly net algorithm does. It subdivides the space around our current point into these carefully chosen regions guided by the structure of the max-min form.
Okay.
And then using that exact stationarity testing oracle, it checks each region for the presence of a near-approximate stationary point.
So instead of just kind of blindly stumbling through the optimization wilderness, we're really using our knowledge of the landscape to guide our search.
Exactly.
With a lever. This leads to a much more efficient, effective way to find those near approximate stationary points.
Exactly. It's all about making those optimization hikes, less strenuous and more purposeful.
We've covered a lot of ground in this exploration of PA functions, from the intricate challenges of stationarity testing to the innovative solutions presented in the paper.
Absolutely.
Maybe we should allow our listeners a moment to digest all this information before we move on to the next part.
Yeah, that's an excellent idea. We've delved deep into the computational complexities and the potential solutions for finding these stationary points in the world of PA functions. There's much more to uncover.
Right.
But a brief pause might be beneficial.
Indeed. It's been a thought-provoking journey so far. When we return, we'll shift our focus to the practical applications of these concepts in the realm of machine learning.
Yes.
Okay. Until then, happy optimizing, everyone.
Let's be optimizing.
All right. Welcome back to our deep dive on piecewise affine functions.
Glad to be back.
We've gone through this theoretical landscape, explored all those unique properties and the complexities of finding those stationary points.
Yeah, absolutely.
And now I really want to see how this theoretical stuff translates into tangible solutions for real-world problems.
Yeah, it's really fascinating how these, abstract math concepts can have such profound implications for practical applications.
Absolutely.
And that's exactly what we're going to be talking about today,
Yeah.
those applications of these insights to specific machine learning challenges.
Excellent. So where do we begin our exploration?
Let's start with a classic problem in machine learning: support vector machines or SVMs.
Yes, SVMs, the workhorses of classification.
Yeah.
All about finding that optimal boundary, right?
Exactly. So imagine you have a collection of data points, and each of these points belongs to one of two categories.
Right.
And the goal of the SVM is to find a line, or in higher dimensions, a hyperplane that neatly divides these points so that you have this clear separation between the categories.
Okay, that makes sense. But where do those PA functions, where do they fit into this? Because SVM seem to deal with linear boundaries, right?
Right, and that's where things get very interesting. So the traditional SVM formulation relies on a loss function that's called the hinge loss.
Okay.
And this hinge loss function is actually piecewise linear,
Okay.
meaning that it's constructed from these straight line segments.
Interesting. So even though we're aiming for this linear boundary,
Mm-hmm.
the underlying loss function itself has this piecewise affine structure.
Precisely. And this has significant implications for finding the optimal solution for the SVM problem.
Right.
So, those pesky stationary points you talked about earlier,
Yeah.
they can be so difficult to find.
Yeah.
They reappear in the SVM world as well.
I see the connection now. So how do those insights that we've talked about PA functions, how do those help us actually tackle this SVM problem more effectively?
So the paper focuses on a specific type of SVM called the margin loss SVM.
Okay.
And it's a variation of the standard SVM that's
Yeah.
designed to be more robust to outlier.
Outliers, those pesky data points.
Exactly.
That throw a wrench in the works.
Exactly. And the margin loss function
Yeah.
used in this type of SVM is also piecewise affine.
Okay.
So the challenge of dealing with those stationary points remains.
Okay, so how do we approach that challenge in the context of SVMs? Does the paper offer any solutions?
So the paper demonstrates how those concepts that we've been talking about, especially like transversality and the subdifferential sum rule,
Right.
can actually be applied to analyze the stationarity properties of this margin loss SVM problem.
So we're basically using those specialized tools that we've developed to gain a deeper understanding of this particular
Exactly.
machine learning algorithm.
Exactly. And this deeper understanding can actually lead to more efficient and effective methods for training SVMs with margin loss.
So it's not just about theoretical elegance. We're really leveraging these insights to make real-world improvements to a widely used algorithm.
Absolutely.
That's impressive. We've seen how our exploration of PA functions can enhance SVMs. What other machine learning problems can benefit from this approach?
Another really interesting application is continuous piecewise affine regression.
Regression,
Yeah.
finding that function that best fits
Exactly.
a set of data points. So in
Yeah.
this case, we're searching for a piecewise affine function that captures those trends in our data.
Exactly. So in continuous piecewise affine regression, we're essentially embracing the flexibility of PA functions,
Okay.
right? Allowing our model to kind of bend and twist to really capture those nuances and complexities
Okay.
in the data. Sometimes a rigid straight line just doesn't cut it.
I see. So we're moving beyond those straight-laced linear models and embracing the curves. But how does the paper connect this regression problem to the concepts we've been discussing?
So the paper demonstrates how the techniques that we've developed for analyzing PA functions can actually be seamlessly applied to this continuous piecewise affine regression problem.
So we can use these tools to really pinpoint the optimal piecewise affine function.
Yes.
That best represents the underlying patterns in our data.
Exactly. It's all about understanding the stationarity properties of this more complex regression model and then leveraging that knowledge to develop efficient algorithms for finding that best fit.
This has been an incredible journey. We've delved into the depths of mathematical theory and emerged with practical tools for solving real world problems in machine learning. It's like we've come full circle.
Absolutely. It really highlights that remarkable interconnectedness, between these abstract math concepts and then their applications in these diverse fields.
Yeah.
And as researchers continue to explore these intricacies of PA functions, we can anticipate even more exciting and unexpected applications to emerge.
It's truly inspiring to see how these seemingly obscure mathematical ideas can blossom into these practical solutions that really shape the world around us.
Absolutely. It underscores the power of curiosity and the importance of pursuing those seemingly, esoteric paths of inquiry. Who knows what other hidden gems are out there waiting to be discovered in the vast landscape of mathematics.
It's been a truly mind-expanding deep dive into this world of piecewise affine functions.
It has.
I feel like we've only just begun to scratch the surface of their potential.
I completely agree. There's always more to learn, more connections to uncover, and more problems to solve.
Absolutely. Well, on that note, it's time for us to bid farewell.
Okay.
But not before encouraging our listeners to keep exploring and questioning and delving deeper into this fascinating world of mathematics and its endless possibilities.
Absolutely. And remember, even the most complex problems can be tackled with the right tools, a curious mind,
Right.
and a healthy dose of perseverance.
That's right. Happy optimizing, everyone.
Happy optimizing.
Welcome back, everybody. Ready for another deep dive? Today we're taking a look at something that sounds kind of simple on the surface. Piecewise affine functions. PA functions for short, but it turns out finding their stationary points can be a real computational puzzle.
Yeah, you hit the nail on the head there. These PA functions, they're everywhere, from optimization problems, to like control systems. Even machine learning models rely on them.
So we're talking like building blocks of complex systems, but with a twist.
Right. You see, at first glance, they seem straightforward. You just take a bunch of straight lines and you stitch them together.
Piecewise, like a quilt. So finding those flat spots, those stationary points, you'd think that'd be a piece of cake, wouldn't you?
You'd think so, but that's where things get really tricky. Sometimes finding those stationary points for PA functions, it's like cracking some of the hardest problems in computer science.
Okay, now you've got me intrigued. Let's start with the basics, though, right? What are we really hunting for when we talk about stationary points in these PA functions?
Well, like with your smooth continuous function, a stationary point is just where the derivative hits 0.
Simple enough.
But PA functions, they've got those abrupt changes in slope where the lines connect, at those stitching points. So traditional methods, they kind of break down.
I see the problem. The subgradient method, that's one of those go-to techniques for stationary points, right? How does that usually work?
So the subgradient method is kind of like taking tiny little steps downhill, always heading in the direction of the steepest descent. Now, for smooth functions, or your convex functions, this method is pretty reliable. You're pretty much guaranteed to end up close to a stationary point after a reasonable amount of time.
But with those PA functions, those seams between the linear pieces, that's where things get messy, am I right?
Exactly.
Yeah.
That subgradient method, it can get stuck bouncing around those seams. It might never actually get near a true stationary point. In fact, 1.2 in our source material actually gives a really good example of this happening.
Oh, this is where the plot thickens. So you're telling me we could do a ton of calculations and still end up nowhere near a true stationary point. That's a little unnerving. So what's this fact 1.2 actually saying?
It basically gives us a reality check. Even with a PA function that looks deceptively simple, something like a 6-Lipschitz function on a two-dimensional plane method, it just can't guarantee we'll get within a certain distance of a stationary point, no matter how long we keep crunching those numbers.
Wow, that really puts things into perspective.
Mm-hmm.
So we need to rethink what it even means to be approximately stationary when we're dealing with these PA functions. But before we go there, let's rewind a bit. Could you remind me about the different types of stationary points we might encounter?
Sure. We've got our local minima, those valleys in the functions landscape.
Okay, those are familiar.
Then you have those fresh stationary points, defined using the Freshet subdifferential. Now, the subdifferential, it captures all the possible slopes you could have at a single point. If 0 happens to be one of those slopes, well, then that point is fresh stationary.
So it's like a local minimum, but maybe not the absolute lowest point across the entire landscape.
Exactly. And get this, for PA functions, fresh stationary points are actually the same thing as local minima. In fact, 2.13 points that out. But when you look at more general functions, they can capture all sorts of interesting behaviors.
Okay, got it. Now, what about those Clark stationary points? They always sound a bit mysterious.
Clark stationary points, well, they use the Clark subdifferential, which is kind of like the fresh one, but it's even more inclusive. Think of it as smoothing out that set of possible slopes by including all their linear combinations.
So like we're taking the convex hull of the fresh subdifferential.
You got it. And because it includes more possibilities, being Clarke stationary is actually a weaker condition than being Fresha stationary, meaning every Fresha stationary point is also Clarke stationary, but not the other way around.
All right, I'm following so far. But our sources, they're hinting that finding any of these stationary points in PA functions can be way harder than we might expect, right?
Yeah, and this is where things get pretty wild. Theorems 3.1 and 3.4, they kind of drop a bombshell. They tell us that testing for even approximate versions of these stationary points, it can be NP hard. And we're talking about PA functions here.
Wait, hold on. NP hard. Now we're talking serious computational heavy lifting.
Yeah.
Can you break that down for those of us who aren't exactly computer science whizzes?
Sure. So NP hard problems, they're basically a whole class of problems that are, well, notoriously tough to solve efficiently. If we could figure out a quick and easy way to solve any NP hard problem, well, then we would have solved one of the biggest mysteries in computer science, whether P equals NP.
Whoa, okay. So you're saying that for some PA functions, even with super powerful computers, finding those perfect stationary points might be practically impossible. That changes everything.
It really does. And to make matters even more interesting, this whole NP hardness thing, it pops up even when the PA functions are represented in seemingly simple forms, like the difference of convex functions, DC, or the maximum of affine functions.
So even if we break the PA function down into smaller, more manageable pieces, it's still ridiculously difficult to find those stationary points.
Yep, that's the crazy part. Take a look at Table 1 in our source material. It really highlights this jump in complexity. It shows that finding local minima for degree 3 polynomials is pretty easy. But for PA functions, which are piecewise degree 1, bam, it suddenly becomes NP hard.
Okay, that table really drives the point home. But if finding exact stationary points is so difficult, does that mean we're just stuck? Is it game over?
Not necessarily. While getting those exact solutions might be computationally off the table, we can still use some clever techniques to get pretty darn close. One of those tricks is called the subdifferential sum rule relaxation, or SRR for short.
Okay, color me intrigued. Tell me more about this SRR. How does it help us navigate this crazy mathematical jungle?
Well, remember, every PA function, it can be expressed as the difference of two convex functions, like h minus g, right?
Right, so we're basically subtracting one nicely behaved function from another.
Exactly. Now, if you try to calculate the subdifferential of this difference directly, that's the ARX, it can be a real pain, a real headache. That's where the SRR steps in. Instead of wrestling with that messy subdifferential, we can ask a simpler question. Is 0 in the difference of the subdifferentials of the individual convex components? 0 minus 0x.
So we're sort of sidestepping the complexity of the whole PA function by looking at the subdifferentials of its parts. Sounds much more manageable.
You got it. That's the beauty of the SRR. But here's the catch. We need to know when the simplification actually gives us the correct answer about those stationary points, and that's where compatibility enters the scene.
Compatibility. Sounds intriguing. I have a feeling we're about to dive into some geometry, right?
You read my mind. Think of compatibility like two puzzle pieces fitting together perfectly. If the subdifferentials of our convex pieces are compatible, then our little shortcut, the SRR, it's going to give us the right answer about those stationary points.
Okay, I'm starting to see the connection. So compatibility is all about how these subdifferentials, which we can picture as geometric, shapes how they relate to each other. But how do we actually check for compatibility in practice?
Great question. Definition 4.6 in the source material, it gives you the formal definition. But, to put it simply, compatibility is about how the tangent cones of those subdifferential shapes intersect.
Tangent cones. Okay, now we're really going deep into the geometry here. Can you unpack that a bit more?
Imagine you're shining a light onto those subdifferential shapes. The tangent cone at a certain point, it captures all the directions you could move from that point while staying inside the shape. Compatibility is all about checking whether those cones intersect in a way that makes the SRR work correctly.
Okay, I think I'm getting the picture. Now, Theorem 4.11, that connects this whole geometric idea back to the analytical world, right? What's it telling us?
It's a big one. It states that for convex PA functions, that magical equivalence between the arrow x and the arrow s minus rx, it holds exactly if and only if those subdifferentials are compatible.
So if we have compatibility, we're good to go. Our shortcut will lead us straight to the right answer about those stationary points. But I'm guessing checking for compatibility directly, especially for those complex shapes, it can be a bit of a computational nightmare, can it?
You nailed it. And that brings us to transversality. Transversality is a more practical condition that's way easier to check than compatibility directly.
Another tool for the toolbox. How does transversality simplify things?
Well, instead of analyzing those intricate tangent cones, transversality just looks at the relationship between the subspaces that are parallel to our subdifferential shapes. Definition 4.15 gives the formal definition, but imagine it like checking if two lines cross instead of lying flat on top of each other.
So we're zooming out a bit, looking at the overall orientation of those shapes rather than their fine details.
Exactly. And the best part is, checking for transversality is something we can do in polynomial-time, according to proposition 4.16. It's much more efficient than digging into the nitty-gritty of compatibility.
I'm all about efficiency. But I'm guessing there's a trade-off, right? Transversality is easier to check, but it probably doesn't always guarantee compatibility.
You're sharp. You're right. Transversality is sufficient, but not always necessary for compatibility. So if those subspaces intersect in a nice way, we know the SRR works perfectly. But if they don't, it doesn't necessarily mean our shapes aren't compatible. We might just need a more sophisticated check.
Can you give me an example where transversality fails, but those shapes are still compatible?
Example 4.22, the one with the tilted squares, that illustrates it perfectly. You've got two compatible polytopes, meaning the subdifferential sum rule holds, but they're not transversal.
So transversality is like a quick and dirty test. Catches a lot of cases, but it might miss a few subtle ones. But then there are those cases where things just line up perfectly right.
Absolutely. When you're dealing with a special type of polytope called a zonotope, transversality and compatibility are actually equivalent. A zonotope, you can think of it as a higher dimensional version of a parallelogram.
So for zonotopes, our shortcut is guaranteed to work without any worries. Always love it when complex concepts simplify so beautifully.
I agree. And this brings up an important point. Even if we had this perfect oracle for testing stationarity, getting those exact stationary points in practice, well, it's practically impossible because of those limitations we have with computers. Rounding errors, finite precision, all that stuff creeps in.
The joys of working with computers. Always chasing those ideal solutions, but never quite reaching them. So how do we deal with this inherent fuzziness?
We need to think about stationarity in a more robust way, one that can handle those real-world imperfections. That's where near-approximate stationarity comes in, or NAS for short.
Okay, Maz, break it down for me.
It's like this. Instead of demanding that a point perfectly satisfies the conditions for stationarity, we give ourselves a little wiggle room. Definition 2.7 lays it all out. A point X is NAS if there's another point Y that's within a tiny distance of X, and that point Y is stationary.
So it's basically saying, as long as we're in the neighborhood of a point that's almost stationary, we're happy.
You got it. It's a more practical approach that acknowledges the limits of what we can actually compute. The question then becomes, how do we find these NAS points, especially when we're dealing with those unruly PA functions?
That's a good question. Our sources mention some algorithms out there, but they seem to rely on assumptions that don't always hold true for general PA functions. Is there a more powerful tool that can handle the wild world of those non-convex PA functions?
There is, and that's where the star of our show comes in, the butterfly net algorithm.
The butterfly net algorithm, I like the sound of that. Tell me more.
It's a robust and efficient way to test for NAS, even for those non-convex PA functions. It's a game changer.
Okay, I'm hooked. How does this butterfly net work its magic?
Picture this. We cast a net that divides the space up into smaller and smaller polyhedra. And these polyhedra, they're carefully crafted to help us zero in on those potential stationary points.
Hold on, polyhedra. Back to those multi-dimensional shapes again. It seems like geometry is popping up everywhere in this problem.
You're right, it is. And as the algorithm breaks down the space, it creates this net that's designed to catch those near stationary points. Hence, the butterfly net.
The name really fits. But how does it actually figure out if a point is NAS?
Well, the butterfly net, it relies on what we call an ONI stationarity testing oracle. You can find the definition in definition 5.1. Think of it as a black box that tells us for sure whether a point is O stationary or not.
An oracle? Sounds almost mystical. So it's like the algorithm asks the oracle, is this point stationary, yes or no?
Exactly. And the cool thing about the butterfly net is that it guarantees one of two things. Either it certifies that a point is NAS, or it gives us a limit on how far away we are from the nearest stationary point.
That's a pretty impressive guarantee. So even if we don't find an exact stationary point, we at least know how close we are to 1.
That's right. And that limit, you can find it in Theorem 5.8. It doesn't depend on where we start our search. That's super important for knowing when to stop running the algorithm.
Okay, this butterfly net algorithm is definitely living up to its name, swooping through the space, catching those near stationary points.
Great analogy. And that wraps up our exploration of the algorithm itself. But there's so much more to explore. We're just getting started.
I'm definitely ready to dig deeper into those applications. Sounds like the butterfly net has the potential to be a real game changer in those fields where PA functions are the name of the game.
For sure. And in the next part of our deep dive, we're going to look at some real-world problems, stuff in machine learning and beyond. Get ready to see the butterfly net in action.
I can't wait. Welcome back to our deep dive into the world of PA functions. Those stationary points, they're still on our minds, right?
Absolutely. I think now's the perfect time to dive into some real-world examples and see how this butterfly net algorithm can really be put to work. You ready to see it in action?
Absolutely. I'm especially curious to see how it handles some of those challenges in machine learning. Our sources mentioned support vector machines, SVMs. Seems like a prime example, wouldn't you say?
You're spot on. SVMs, specifically those that use what we call a margin loss function, are a great place to start. This particular kind of SVM is known for being pretty robust when it comes to dealing with outliers. You know, those data points that just don't quite fit the pattern.
Outliers.
Ah.
The bane of every data scientist's existence, I'd say. They always seem to mess things up.
That's for sure. And it turns out that the objective function for a margin loss SVM, it's laid out in section 6.1. Well, it has a PA component. No surprises here, finding those stationary points can get pretty tricky.
So this is where our butterfly net swoops in for the save, ready to snag those near stationary points.
Exactly. The thing about the butterfly net is it works best with PA functions that are expressed as the difference of two convex functions.
Right, we talked about that.
And lucky for us, we can actually rewrite the objective function of a margin loss SVM in that exact form. Convenient. So we can just tailor the butterfly net to handle this specific SVM problem just like that.
Precisely. And if we apply what we know about compatibility and transversality, we can actually figure out when that subdifferential sum rule holds for the SVM's objective function. This helps us know when we can trust the butterfly net to give us those really accurate results.
I love how we can use these abstract mathematical concepts and actually apply them to solve problems in machine learning. It's pretty cool.
It really shows you how interconnected different fields of math can be. Speaking of connections, let's switch gears a bit. Let's look at another application that highlights just how versatile this butterfly net can be. Continuous piecewise affine regression.
Continuous piecewise affine regression. Okay, help me visualize this. I'm thinking something like those connect the dots puzzles, but instead of drawing a smooth curve, we're connecting the dots with straight lines, right?
That's a perfect way to picture it. Instead of fitting a smooth curve to the data, we're basically approximating it with a bunch of connected line segments, like building a simple piecewise linear model. And I'm guessing finding those best fit lines, those spots where the model is stationary, that's where traditional methods might hit a wall, am I right?
You got it. Section 6.2 of our sources breaks it all down formally. We've got this objective function that measures the error between the model's predictions and the actual data. And guess what? This objective function, just like in the SVM case, has those PA components that make finding those stationary points a real pain.
But wait a minute, haven't we been saying that a lot of these problems can be rewritten as the difference of two convex functions? Didn't we talk about that earlier?
You're catching on quick. Yes, we can apply a similar kind of transformation to this continuous piecewise affine regression problem. And once we get it into that familiar difference of convex form, guess who's ready to take over? The butterfly net. It can help us track down those near-approximate stationary points.
It's impressive how this algorithm can be adapted to handle all sorts of different problems. It's like this universal tool for anything involving PA functions.
It really is a powerful tool. And while we've been focusing on machine learning, you can use the butterfly net in any field where you find PA functions. Things like optimization problems, control systems, even economics.
Okay, you've convinced me. The butterfly net is a rock star. But our sources, they also mention some unanswered questions and some areas for future research, don't they? What are some of the things researchers are still trying to figure out?
Well, Remark 5.9 asks a pretty intriguing question. Can we stretch this butterfly net to work with other types of stationary points beyond just Clark stationarity? Remember those different flavors of stationarity we talked about earlier?
Yeah.
Researchers are wondering if we can tweak the butterfly net to handle those nuances, too.
So it's like refining our net, making it even better at catching different kinds of flatness in those functions, right?
Exactly. And another head scratcher is whether those NP hardness walls we bumped into, whether they still stand when we fix the input dimension of the PA function. Does making the problem smaller actually make it easier to solve?
It's like asking, if we shrink down our puzzle, does it become easier to put together? Common sense says yes, but maybe the math has a different answer.
That's the beauty of research. Sometimes our intuition is right, sometimes it takes us in unexpected directions, and then there's the ultimate challenge. Can we develop techniques to test stationarity in any piecewise smooth function, not just PA functions?
Whoa, now that's ambitious. Building a butterfly net that can catch stationary points in any mathematical landscape.
It's a tough goal, but the potential payoff is huge. Imagine the impact on things like robotics, economics, climate modeling. The possibilities are endless.
Now I'm really starting to see the potential of this research. It's
There-
exciting stuff.
Absolutely. And even though our focus here is on PA functions, the bigger picture is about understanding and navigating those complex, non-smooth landscapes. That's a fundamental challenge in so many fields.
It feels like we're just beginning to explore the depths of this topic. So much more to discover.
I agree. And as we develop better tools and techniques, who knows what amazing breakthroughs are waiting for us.
Well, with that sense of wonder and possibility, I think it's time to wrap up this part of our deep dive into the world of PA functions and those tricky stationary points. I'm feeling really inspired by everything we've learned and the potential for future discoveries.
Me too. It's been quite a journey. And in the final part of our deep dive, we'll bring all these insights together and leave you with some food for thought, some questions to ponder on your own. Stay tuned.
Welcome back, everyone. We've been on quite the adventure, haven't we? Exploring the world of PA functions, those seemingly simple functions that turn out to be quite complex when you try to find their stationary points.
It's been a wild ride. We've run into computational roadblocks, discovered clever workarounds, and even built ourselves a butterfly net to catch those slippery near-stationary points.
I'm still amazed by how much depth we found in a problem that seems so straightforward at first glance.
That's the beauty of math. There's always more than meets the eye. But before we wrap things up, let's take a step back and think about what we've learned. What were some of those aha moments for you? Those moments that really shifted your understanding?
For me, it was realizing just how tricky it can be to find those stationary points in PA functions. Those NP hardness results we talked about, theorems 3.1 and 3.4, those were eye-openers for sure. They showed us that for certain PA functions, finding those perfect stationary points might be impossible, even with all the computing power in the world.
I agree. Those theorems were game changers. They forced us to shift our thinking and embrace the idea of finding approximate solutions.
And that's where the subdifferential sum rule relaxation came in, right? The SRR. It was like finding a secret path through a dense forest of math.
Exactly. The SRR cleverly uses the fact that PA functions can be expressed as the difference of two convex functions. By focusing on those simpler components, it gives us a way to get close to those stationary points without all the computational headaches.
But that path wasn't always easy to find. We needed the right key to unlock it, and that key was compatibility.
Ah, yes, compatibility. That's where geometry and analysis meet, and it's a beautiful thing. Theorem 4.11 showed us that if those subdifferentials fit together just right, if they're compatible, then our shortcut, the SRR, gives us the right answer about those stationary points.
I loved how that theorem connected those abstract geometric shapes to the analytical properties of the function, like seeing two different languages suddenly translate into each other.
Absolutely. But checking for compatibility directly can be pretty computationally expensive, especially for complex shapes. That's where transversality stepped in, a more practical condition that's easier to check.
Transversality was like trading a complex map for a simple compass. It gave us a quick way to see if our shortcut would likely work.
Exactly. And while transversality doesn't always guarantee compatibility, it does for special cases like those zonotopes. Remember those nicely structured polytopes that make things a bit easier.
I always appreciate those moments in math where things just click into place. But even with all those clever techniques, we can't escape the limitations of working with computers. Rounding errors and finite precision always add a bit of fuzziness.
True, we have to accept that we're dealing with approximations and adopt a more flexible notion of stationarity, near-approximate stationarity, or NOUS.
It's like acknowledging that in the real world, we often have to work with a bit of uncertainty. We can't always expect perfect answers, but we can get close.
And that's where our butterfly net comes in, turning those theoretical insights into a practical tool for finding those near stationary points.
I'm still in awe of how elegant that algorithm is. It's like casting a net that gradually subdivides the space, catching those elusive points with increasing precision.
It really showcases the power of combining geometric intuition with rigorous mathematical analysis.
But as with any deep dive, we're left with some lingering questions. What are some of the open problems that researchers are still working on?
Well, one interesting question is whether the butterfly net can be extended to handle other types of stationary points beyond Clark's stationarity. Can we make our net even more sensitive to subtle variations in the function's behavior?
So it's like asking if we can build a net that can catch not just butterflies, but all sorts of interesting creatures.
Exactly. Another question is whether those MP hardness barriers become less formidable when we restrict the problem to a specific number of dimensions. Does reducing the complexity of the space make the problem fundamentally easier?
It's like trying to solve a puzzle. Does it get easier with fewer pieces? You'd think so, but math can be full of surprises.
And then there's the ultimate challenge. Can we develop methods to test stationarity in any piecewise smooth function, not just those PA functions?
Now that's a grand ambition. It's like creating a universal butterfly net for any mathematical landscape.
These are just a few of the exciting areas for future research. As we keep developing new tools and techniques, who knows what amazing discoveries are waiting for us?
It's inspiring to see how this research is pushing the boundaries of what's possible. Our journey into the world of PA functions has just begun.
Absolutely. And with that, we wrap up our deep dive into the world of PA functions, those stationary points, and the fascinating interplay of geometry, analysis, and computation.
We've seen how seemingly simple problems can be deceptively complex, how clever solutions can overcome computational obstacles, and how new algorithms like the butterfly net can help us unlock a deeper understanding of these intricate mathematical landscapes.
Until next time, keep those minds curious and never stop exploring.
Farewell, fellow knowledge seekers. Welcome to today's deep dive, where we're going to be tackling a pretty fascinating topic.
Yeah, fascinating and a little bit tricky.
Yeah, it is a bit of a brain twister. We're going to be looking at stationary points in piecewise affine functions.
Ah, PA functions, right. Yeah, these things they seem simple on the surface, but
Deceptively so.
yeah, exactly, deceptively, so they can get really complex when you start digging into the math behind them.
It's kind of like one of those optical illusions
Yeah.
where it looks straightforward at first glance, but then you
Yeah.
realize how much is actually going on.
Exactly. And the research we're looking at today really brings some of that complexity to light, particularly when we're talking about finding these stable points, these stationary points.
Right, and it's not just theoretical. This has like really big implications for things like machine learning, where
So
PA functions are everywhere.
yeah, they pop up all over the place in algorithms, and we need to be able to understand these stationary points to make these algorithms work well.
So let's dive into some of these papers you shared. The first one, on the intractability of finding stationary points of piecewise affine functions. That title alone is a mouthful.
Yeah, it sets the stage though for just how tricky this problem can be.
Yeah, and they hit us with some pretty startling results right off the bat, like this idea that even determining if a point is approximately stationary can be like computationally nightmarish.
Yeah, that's theorem 3.1 in the paper, and it's something that really, makes you step back and think, okay, we got to be careful here. It says that for PA functions, just determining if a point is epsilon stationary, so within some tolerance, is actually strongly NP hard.
Okay, so hold on. Even getting close to a stable point
Right?
in these seemingly simple functions is like really hard.
Yeah.
That's a big deal. So for those of us who aren't, complexity theory gurus, what does strongly NP hard actually mean? Like, what are the implications there?
Okay, so NP-hard in essence means that we don't have any algorithms we know of that can solve this problem efficiently, like in a reasonable amount of time as the problem gets bigger. And the strongly part really just emphasizes that this difficulty sticks around even if we're willing to accept some approximation, like even if we're okay with being close to the answer, it's still really hard to find.
Wow. Okay, that's a pretty big hurdle, especially when you consider, how prevalent these PA functions are. So we've got this problem. And then they also talk about the limitations of the subgradient method, which, is like a classic workhorse for optimization. So remind me, why does that struggle with PA functions?
Okay, so the subgradient method is a go-to for non-smooth optimization, where you don't have these nice derivatives everywhere. And it works by kind of taking steps in the direction of the negative subgradient. But the problem with PA functions is they've got these flat pieces, right?
Yeah, like those flat plateaus.
Exactly. And on those flat pieces, the subgradient can actually be 0, even at points that aren't truly stationary.
Wow.
So the algorithm can kind of get stuck. It's like it hits this flat spot and thinks, oh, I'm at the minimum, but it might not be the actual minimum.
Right, like our hiker gets to the plateau.
Exactly.
And thinks they're at the lowest point.
Yeah, and what's fascinating is the paper actually gives us a concrete example of this. In fact, 1.2, they show that even for a really simple PA function, just 2 dimensions, the subgradient method can be fooled for like an arbitrarily long time.
So it could just be wandering around forever, basically.
Yeah, essentially. And that really highlights, the limitations we're dealing with here.
So subgradient method, maybe not the best tool for this job, at least not without some serious modifications. So what other avenues do they explore in this research for tackling this stationary point problem?
Well, one thing they do is they look at how the way we represent these PA functions can impact the complexity of finding these stationary points. And they focus on 2 main representations, the difference of convex or DC representation and the max-min form.
Okay, so break those down for us. What do those look like and how do they connect to these complexity results?
So the DC representation, it's kind of like what it sounds like you're expressing the PA function as a difference of 2 convex functions.
Okay.
Now, convex functions are nice to work with because...
Yeah, they have that nice property.
Exactly. Any local minimum is also a global minimum.
Right. Much easier to optimize.
Exactly. And what they show in the paper is that for PA functions in this DC form, figuring out if a point is a local minimum is what we call co-NP complete.
Okay.
And that basically means it's about as hard as verifying a solution to an NP-complete problem.
So even for this potentially simpler task,
right,
we're still hitting those computational roadblocks.
Exactly. Now, with the max-min representation, it's a bit different here. You're expressing the function as the maximum of a bunch of minimums of functions.
So it's like we're taking our Lego landscape and we're dividing it up into these little regions, and each region is defined by like the lowest of several planes.
Exactly, you got it. And what they prove for PA functions in this max-min form is that determining if a point is a stationary point is straight up NP complete.
Okay, so no matter how we slice it,
yeah,
it's a tough problem.
It seems to be. Yeah, and it doesn't really matter which representation we choose. We're still going to run into this inherent difficulty.
It's like this persistent problem that just keeps rearing its head. They go through a lot of really intricate mathematical arguments to arrive at these complexity results. Are there any particular proofs or concepts that you found particularly illuminating or elegant in the way they approached it?
One of the most insightful parts for me was the proof of theorem 3.1, where they established that strong NP hardness of determining epsilon stationarity. And they do this by cleverly constructing a reduction from the 3SAT problem.
Right, 3SAT, that's like the classic example of an NP-complete problem.
Exactly. And what they essentially show is that if we could solve the epsilon stationarity problem for PA functions efficiently, then we could also solve 3SAT efficiently.
Which we don't think we can do.
Exactly, which would kind of break our whole understanding of how these complexity classes work.
Right. It would be a huge breakthrough if we could.
Absolutely. And the paper doesn't stop there. It goes on to really dive into the specifics of the DC and max-min representations. And they prove co-NP completeness for local minima in the DC case and NP completeness for general stationary points in the max-min case. So it's like they're really building this comprehensive understanding of the computational landscape surrounding these functions.
Yeah, they're really painting this detailed picture.
Exactly.
Of all the challenges.
Yeah, and what's really cool is that the proofs for these specific cases, they involve totally different techniques. They leverage the properties of convex sets polyhedra, and it really shows the depth of the mathematical tools that they're using to analyze these problems.
It's like they're pulling out all the stops to really understand these PA functions.
Yeah, it's a testament to the power of theoretical analysis, to really uncover these complexities and give us insights that can help us build better algorithms down the line.
Okay, so we've established that finding those stationary points in PA functions, it's no walk in the park.
Right.
Even approximately so. Is there any hope? Is there any way to actually find practical solutions? Are we doomed to wander aimlessly in this complex landscape?
Well, the research doesn't leave us completely empty-handed. It offers a few glimmers of hope. And one of the most promising avenues is this idea of using the subdifferential sum rule, which is a tool from calculus.
Okay, so remind us what that rule is all about and why it might be helpful here.
So the subdifferential sum rule basically says that under certain conditions, the subdifferential of a sum of functions is equal to the sum of the subdifferentials of those individual functions.
Okay, so we can break down our complicated PA function into smaller pieces.
Exactly.
Analyze those.
That's the idea. And if we could do that, it could really simplify things. But of course, there's a catch.
There's always a catch, right? What's the catch here?
The catch is that this rule doesn't always work for non-convex functions, and unfortunately, our PA friends aren't always convex.
Oh, right. So it's like we're trying to build a Lego structure by only looking at the individual bricks without considering how they fit together.
That's a great analogy. Yeah, you might end up with something that doesn't quite work.
Right, exactly. So how do they get around that?
Well, this is where it gets really interesting. They actually dive into the specific conditions under which this subdifferential sum rule does hold for PA functions, and they introduce this new concept called compatibility.
Compatibility, okay.
Yeah, and it basically describes the geometric relationship between the subdifferentials of the pieces that make up the PA function.
Okay, so if the pieces are compatible,
Right.
we can use the rule.
Exactly.
Okay, but how do we check for compatibility? Could that be as hard as the original problem?
That's a great question, and that's something they address in the paper. Directly verifying compatibility can be computationally expensive, but they introduce this other condition called transversality.
Okay, transversality. Give us the intuition there. What is that all about?
Think of it like a shortcut to checking for compatibility. It's a sufficient condition. So if transversality holds, then we know compatibility holds, and the best part is that transversality is much easier to check computationally.
Oh, so it's like a quick and easy test.
Exactly.
We can run to see if we can use the sum rule.
Precisely.
Are there any cases where transversality is not just sufficient, but actually like equivalent to compatibility?
Yeah.
Where checking one is the same as checking the other?
There is, and it involves a special type of polytope called a zonotope.
Zonotope.
Yeah, these things have a really nice geometric structure that makes them particularly well behaved when it comes to this stuff. So when we're dealing with zonotopes, transversality, and compatibility, they're basically the same thing.
So if we're lucky enough to be working with zonotopes, we can breathe a sigh of relief.
Exactly. And even if we're not, transversality still gives us a really powerful tool to simplify things and potentially make some progress on this really hard problem.
This is all incredibly insightful, but before we jump into like the algorithmic solutions that they present in the research,
Yeah.
there's one more concept that caught my eye, near-approximate stationarity, the NAS thing.
Mm-hmm.
Can you explain what that is and why it's relevant, practically speaking?
Of course. So, in the real world, we rarely find exact solutions. There's always some noise, some limitations in our algorithms. And as it acknowledges that, it says, hey, we're not looking for perfection. We just want to be close enough.
Right, like in the real world.
Exactly.
Good enough is often good enough.
Exactly. And what it means is that we're aiming for a point that's within some predefined error bounds of an actual stationary point.
Okay, so how do we know when we're close enough? How do we actually determine this NAS thing?
That's a great question, and that's where the research really shines. They introduced this really groundbreaking algorithm that can efficiently certify or refute this NAS condition for a given point.
So it's like this algorithm can actually tell us if we're close enough.
Yeah, it's like having this high-tech measuring tool that can tell us, hey, you're within tolerance, or nope, you're still too far off.
Now, wait a minute. Does this algorithm actually solve that NP hard problem that we were talking about earlier?
Not quite. It relies on what we call a testing oracle.
Okay.
And this oracle can check for exact stationarity. And we know that might be a hard problem in itself. But the beauty of the algorithm is that it doesn't try to solve that hard problem directly.
Right. It uses it as a tool.
Exactly. It uses it as a black box and says, okay, oracle, tell me if this point is exactly stationary. And then based on that answer, it cleverly navigates the PA function to figure out if we're close enough to a stationary point.
So it's like we've got this super precise GPS that can tell us if we're standing on the exact peak of a mountain, but we're trying to find a spot that's just high enough without necessarily needing to reach the absolute summit.
I love that analogy. Yeah, that's a great way to think about it. And this algorithm gives us a way to do just that.
So it's like we're following these clues, and each oracle call is like a new clue that helps us get closer to our goal.
Exactly.
Amazing. And this leads to a reliable stopping rule, right?
Right.
No more getting stuck wandering around forever.
Exactly. And that's where we'll pick up in Part 2 of our deep dive will actually explore the inner workings of this algorithm in more detail, and we'll see how it connects to real-world applications in machine learning.
This is fascinating stuff.
I'm
already hooked.
I'm excited to dive deeper into it with you.
All right, so let's dive into this groundbreaking algorithm you were talking about. This sounds like it's a real game changer for working with PA functions.
Yeah, it really is, and the way it uses this testing oracle is super clever.
Yeah, before we get too deep into the weeds, remind us what that testing oracle is and why we need it in the first place.
Okay, so the testing oracle, you can think of it as this like black box that we can ask, hey, is this point an exact stationary point of our function?
Mm-hmm.
And it'll give us a yes or no answer.
Okay, and we need that because figuring that out ourselves is that really hard NP hard problem we talked about.
Exactly, and that's why this algorithm is so clever. It doesn't try to solve that hard problem head on. It kind of sidesteps it.
It uses it as a tool.
Yeah, exactly. It uses the oracle as a tool to help us find those near approximate stationary points without getting bogged down in the complexity of finding the exact one.
So it's like we have this super precise GPS that can tell us if we're standing on the exact peak of a mountain, but we're okay with just finding a spot that's high enough without needing to reach the absolute summit.
Perfect analogy. That's exactly it. And this algorithm gives us a way to do just that.
I love that. So this algorithm, it gives us a set of rules for navigating this PA landscape. And we use the oracle sparingly just to get those key pieces of information we need.
Exactly.
Okay, and we're trying to find those points that satisfy that NAS condition, right?
Yes, exactly. We want to be close enough to a true stationary point.
Close enough for practical purposes.
Right.
Okay, so how does this algorithm actually work? How does it use these oracle calls to find those points?
So at its core, it involves dividing the domain of our PA function into a bunch of different regions.
Okay, like we're splitting up our Lego landscape.
Exactly. And the algorithm kind of goes through these regions one by one and uses the oracle strategically to determine if a point falls within a region that we know contains a near approximate stationary point.
Okay, so if we're in the right region, we know we're close enough.
Exactly.
And that's where the enough's guarantee comes in.
Precisely. And the way these regions are constructed and analyzed is where the real magic happens. It relies on this concept from convex analysis called the epsilon subdifferential.
Okay, epsilon subdifferential. Remind us what that is.
Right. So the epsilon subdifferential, it basically captures all the possible subgradients of our function within a small epsilon neighborhood around a given point.
So instead of just looking at the subgradient at a single point, we're looking at a whole bunch of them.
Yeah, like a little cloud of subgradients.
Right. Okay, so why is that helpful?
Well, it turns out that if this epsilon subdifferential contains the zero vector, it tells us that there's a point nearby that's epsilon stationary.
Ah, I see. So it's like a signal that we're in the right neighborhood.
Exactly. And the algorithm uses this information to kind of zero in on those promising regions.
So it's like a detective using clues to narrow down the list of suspects.
I like that analogy. Yeah. And the algorithm, it systematically goes through these regions and it either finds a point that's NS, or it tells us that, nope, there's definitely no such point in this region.
So it gives us this really strong guarantee.
Right.
Either we found what we're looking for, or we know for sure that it's not here.
Exactly. And this is a huge improvement over just blindly applying traditional optimization methods.
Okay, so this algorithm sounds amazing in theory, but how does it actually connect to real-world problems, especially machine learning?
Right. So one really cool application is in training support vector machines, or SVMs.
Right, SVMs, we talked about those earlier.
Yeah, and remember how we mentioned that the row margin loss function that's often used in SVMs can be expressed as a PA function?
Yeah, I remember that.
Well, now we can use this algorithm to more reliably and efficiently find those near approximate stationary points of that loss function.
Oh, so we're directly improving the training process of SVMs.
Exactly, and that leads to more effective models.
Wow. Okay, so that's one example. Are there other areas where this algorithm is having an impact?
Oh, absolutely. Another one is in piecewise affine regression.
Okay.
Remember, that's where we're fitting a series of line segments to our data instead of just a single straight line.
Right, so it's like a more flexible form of regression.
Exactly. And the objective function that we're trying to minimize in that case is also a PA function.
Oh, I see.
So you can use this algorithm to find good solutions.
Okay, so it sounds like this algorithm is pretty versatile.
It really is, and we're still just scratching the surface of its potential applications. I think we'll see it popping up in more and more areas as researchers continue to explore its capabilities.
This is all super exciting. But I do want to circle back to something you mentioned earlier about the computational cost of that testing oracle. Can you elaborate on that a little bit?
Yeah, sure. So remember, we're assuming that this oracle can solve the exact stationarity problem.
Right, which we know is hard.
Exactly. It could be NP hard. So even though the algorithm itself is efficient, those oracle calls could become a bottleneck.
It's like we're trying to optimize the optimizer itself.
Yeah, exactly. And that's why a lot of current research is focused on developing more efficient oracles that can exploit the specific structure of certain types of PA functions to speed up those computations.
So it's like finding better tools to help us solve the problem even faster.
Precisely. And as we develop those better tools, the practical applicability of this algorithm will only continue to grow.
This has been a really illuminating discussion.
Hmm.
I'm blown away by how these theoretical insights can lead to such practical and powerful tools.
Yeah, it's amazing to see how these different areas of math and computer science come together to solve real-world problems.
It really is, and I'm excited to see what the future holds for this line of research.
Me too. It's a really exciting time to be working in this field.
Man, we've covered a lot of ground today. It's been a real whirlwind tour of PA functions and all the complexities that come with them.
Yeah, it's been quite a journey. We started with the basics, then uncovered these surprising computational challenges, and then ended up with these really clever solutions.
Yeah, and that algorithm we talked about in part 2, that was the real highlight for me. The way it uses that testing oracle to find those near-approximate stationary points, it's like a whole new way of thinking about optimization.
I agree, it's a real game changer, and I think it has the potential to revolutionize the way we approach these kinds of problems, not just with PA functions, but in all sorts of areas.
Yeah, before we wrap up, I want to dig into some of the finer points of this algorithm and really explore what it means for the future of machine learning and beyond.
Sounds good. Let's do it.
One thing that really struck me was the way it navigates the PA landscape. It's like it's playing this strategic game where each oracle call is a calculated move.
That's a great way to put it. It's not about brute force. It's about making smart decisions based on the information we have.
Right. It's like we're following these clues, and each oracle call reveals a little bit more of the map.
Exactly. And the algorithm is designed to make the most of each clue. It uses geometric insights and the concept of the epsilon subdifferential to eliminate dead ends and focus on the most promising paths.
Now, remind me again about that epsilon subdifferential. What's the intuition there?
So the epsilon subdifferential, it's basically like looking at all the possible subgradients of our function within a small neighborhood around a point. So instead of just considering a single subgradient, we're getting a broader picture of the local behavior.
Right. So it's like getting a feel for the terrain around us instead of just looking at a single point.
Exactly. And this information is crucial for the algorithm to decide whether a region is worth exploring. If the epsilon subdifferential at a point contains the 0 vector, it means there's a good chance of finding a near-approximate stationary point nearby.
Ah. So it's like a green light that tells us, hey, keep going this way. You're on the right track.
Exactly. And by combining this information with those strategic oracle calls, the algorithm can navigate even really complex PA landscapes efficiently.
It's like a master detective, using both deduction and a limited amount of forensic evidence to solve a case.
I love that analogy.
Yeah.
And the implications of this go far beyond just PA functions. This algorithm has the potential to change the way we think about optimization in general.
Let's talk about those implications, especially in the context of machine learning. We already mentioned how it can be used to improve things like support vector machines and piecewise affine regression.
Right. But those are really just the tip of the iceberg. I think this algorithm can inspire a whole new generation of machine learning algorithms and techniques.
Can you give us a glimpse into what those new frontiers might look like?
Well, one area I'm really excited about is deep learning. Deep neural networks are notoriously difficult to optimize. Their lost landscapes are often riddled with all these non-convexities and local minima.
Right? And traditional gradient-based methods can easily get stuck in those minimally.
Exactly. And that's where this algorithm could be a game changer. Its ability to find near-approximate stationary points, even in those tricky non-convex settings, could lead to much better performance for deep learning models.
So instead of settling for a solution that's good enough, we could potentially find solutions that are much closer to the true optimum.
Exactly. And that could have a huge impact on everything from image recognition to natural language processing.
It's amazing to think about how this seemingly abstract mathematical concept could unlock so much potential in AI.
It really highlights the power of theoretical research. You never know what practical applications might emerge from these deep mathematical insights.
So as we wrap up our deep dive, what are some of the key open questions or areas of future research that you're most excited about?
Well, one area that's really important is developing even more efficient testing oracles. Remember we talked about how the computational cost of those oracle calls can be a bottleneck?
Right. So if we can make those oracles faster, the whole algorithm becomes even more powerful.
Exactly. And there's a lot of exciting work happening in that area, exploring new techniques to speed up those computations by exploiting the specific structure of certain PA functions.
Another thing I'm curious about is how we can extend these ideas to handle even more complex function classes. PA functions are just one type of non-convex function, and there's a whole world of other functions out there that pose similar challenges.
Absolutely. I think the insights and techniques we've developed for this algorithm can serve as a blueprint for tackling those more general cases.
It's like we're building a whole new toolbox for optimization, and who knows what amazing things we'll be able to build with it.
Exactly. The possibilities are endless, and that's what makes this field so exciting.
Well, this has been an incredible journey of exploration and discovery. I feel like we've barely scratched the surface, but it's definitely left me wanting more.
Me too. And I hope our listeners feel the same way.
To everyone who tuned in, thank you for joining us on this deep dive into the fascinating world of PA functions and near-approximate stationarity.
We hope you've enjoyed the ride.
And we'll see you next time for another deep dive into the world of cutting-edge research.
Keep those minds curious.
Welcome to another deep dive. Today, we're going to be venturing into the world of piecewise affine functions.
Okay.
And the quest for their stationary points.
Yeah.
We'll be dissecting a research paper called Testing Approximate Stationarity Concepts for Piecewise Affine Functions by Tian and Anthony Man-Cho. So, published January 7th, 2025.
That's good.
So it's a fascinating area of research.
Yeah, it really is.
That blends optimization, computational complexity, and a touch of geometric intuition. Right.
It's a great mix.
And for you listening in, we know you're no stranger to the intricacies of mathematical analysis.
Yeah.
So we'll be delving into the nitty-gritty details, exploring the proofs,
Yes.
and appreciating the elegant interplay of concepts.
Exactly.
So to set the stage, piecewise affine functions, or PA functions as they're often called, are essentially functions built from linear segments, like connecting straight lines with sharp corners.
Right, exactly.
They pop up everywhere in optimization problems, economic models, even neural networks.
You see them all over.
Yeah, they're like the building blocks of more complex systems, and understanding their behavior, especially finding those flat points where the function doesn't change. Those stationary points is crucial for optimization.
Absolutely.
Now, finding stationary points for smooth functions is relatively straightforward.
Yeah.
Right? We can use derivatives.
Right.
But PA functions, with their sharp corners and non-differentiability, pose a unique challenge, and that's where the concept of approximate stationarity comes in.
It's a whole different ballgame.
It's like saying, okay, we might not be able to hit those stationary points perfectly, but how close can we get?
Yeah.
And how do we even define closeness in this context?
Exactly. And that's what this paper dives into.
Yeah.
The paper really dives deep into the computational complexity of finding and verifying these approximate stationary points. And the results are quite surprising.
Okay, so the paper starts by exploring the limitations of a well-known optimization method called the subgradient method.
Yes.
It's a workhorse for dealing with non-smooth functions. But even this powerful tool has its limits when it comes to PA functions.
It does. It does.
So fact 1.1 in the paper highlights that under certain conditions, the subgradient method does converge to what's called a Clark stationary point. But there's a catch. This convergence is asymptotic.
Right.
Meaning it only holds as we take an infinite number of steps.
That's right.
Right? And in the real world, we have finite computational resources and time constraints to this asymptotic convergence. Well, theoretically interesting isn't very practical.
Not very practical,
And what's even more striking is fact 1.2, which cites theorem 2 from a previous work. And this theorem states that there's no algorithm, no matter how clever, that can guarantee finding a stationary point for a PA function in a finite number of steps.
That's a big deal.
It's a pretty profound statement.
Yeah.
You know, it means we're fundamentally limited
Yeah.
in our ability to find exact solutions.
Right.
So what does that mean for us practically?
Yeah.
If we can't guarantee finding a stationary point in a fixed number of steps, what kind of strategies can we use?
It forces us to think differently.
Yeah.
It forces us to reevaluate our goals and focus on approximate solutions. Instead of seeking those elusive exact stationary points, we must ask, how close can we get? And can we verify that we're indeed close enough?
That's a good point.
Yeah,
So this leads us to the heart of the paper,
it does.
exploring the world of approximate stationarity and its computational challenges.
It's a whole new world.
So the authors dive into various definitions of approximate stationarity, each with its own nuances and complexities. And surprisingly, even testing for simple versions of these approximate stationary points turns out to be incredibly difficult.
Okay, I'm intrigued.
Yeah, it's interesting stuff.
Can you give us a concrete example of how tricky these problems can get?
Absolutely.
So, let's consider the seemingly straightforward task of determining whether a point is a local minimum,
Okay.
a point lower than all its neighbors.
Mm-hmm.
Now, for smooth functions, this is relatively easy,
Yeah.
but for PA functions, the paper shows that it's co-NT hard,
Oh, wow.
even for simple PA functions.
Now, I know our listeners are comfortable with complexity classes,
Yeah.
but just for clarity, co-NP hard problems are essentially those where it's really difficult to prove that something isn't true.
Right.
In this case, it means proving that a point is not a local minimum can be computationally infeasible.
Exactly.
So even if you stumble upon a potential solution,
Yeah.
confirming that it's not what you're looking for can require checking an enormous number of possibilities,
It can be a nightmare.
making it practically impossible for most real-world scenarios.
Exactly.
So even a simple question like,
Yeah.
is this a local minimum,
Right.
can lead us down a computational rabbit hole.
It can. It can.
And it doesn't stop there. The paper also establishes that determining if a point is a general stationary point,
Okay.
not just a local minimum, is NP hard.
It's even harder.
This means that even finding a solution, let alone verifying it, is incredibly difficult.
It really is.
So to emphasize the contrast,
Yeah.
finding stationary points for those smooth, well-behaved functions is like a walk in the park,
I like that analogy.
compared to navigating the rugged terrain of PA functions.
It's very true.
A perfect analogy.
Yeah.
So smoothness makes a world of difference in computational complexity.
It really does.
For PA functions, we're in a whole different ballgame.
A whole different ballgame.
All right, so I'm starting to grasp the magnitude of the challenge,
Good.
but our listeners are mathematically inclined.
Yes, they
They
are.
want to understand the how and why.
Of course.
Can we delve into the specifics of how the authors prove these hardness results? I believe it involves a clever technique called reduction.
Yes, it does.
So it's like saying, if you can solve this seemingly niche problem with PA functions, you've essentially unlocked a solution to a whole class of incredibly hard computational challenges.
It's like a master key.
Exactly.
Yeah.
And that's what makes these reduction arguments so powerful.
They are powerful.
They established a concrete link between seemingly disparate problems, highlighting the inherent complexity of the problem at hand.
They really do connect the dots.
Can you walk us through the basic idea behind these reductions?
Sure.
Without getting too lost in the technical weeds?
I'll try my best.
Okay.
So for the local minimum case, they use a problem called PAR1011EPX1.
Okay.
Now, imagine you have a bunch of vectors, and each component of these vectors can only be -1, 0, or 1.
Okay.
This problem asks, can we combine these vectors in a way that maximizes their total length when measured using what's called the O1 norm?
Okay.
So it's like arranging these vectors to stretch out as far as possible in all directions.
I got it.
Now, the authors cleverly construct two specific PA functions,
Okay.
HF and GF, such that finding a local minimum of their difference, HF-GF, is directly equivalent to solving that PAR101 MHX1 problem.
So they've cleverly embedded the complexity of a known hard problem into the structure of these PA functions.
That's right.
If you could find that local minimum easily,
Yeah.
you'd essentially be solving PAR101 MHX1, which we know is a computationally hard nut to crack.
You got it.
And they don't just claim this, they prove it rigorously.
Rigorously.
They show that if you can find a local minimum of HFGF, you can extract a solution to PAR101 MX1.
Yeah.
And conversely, if PAR101 MX1 has a solution,
Right.
then HFGF must have a local minimum.
It's a two-way street.
So it's a two-way street, a tight connection between the solutions of these two problems.
That's it.
And since we know solving PR101 MAX1 is co-NP hard, finding that local minimum for our PA function must be at least as hard.
That's the logic.
Precisely. This reduction argument firmly establishes the co-NP hardness of finding a local minimum for a PA function.
It's a solid argument.
Okay, that's the local minimum case.
Yeah.
But remember, the general stationary point case is even harder. It's NP hard.
Right.
How do they demonstrate that? I believe they introduce a rather intriguing seesaw gadget.
They do.
You're exactly right. They construct a special mathematical object.
Yeah.
This seesaw gadget.
It's a clever tool.
Built from two convex PA functions, cleverly designed to mimic the behavior of a seesaw balancing at its center. I love the visual imagery. A mathematical seesaw.
Yeah, it's a good one.
Teetering on the edge of stationarity.
I like it.
And here's the key insight.
Okay.
The behavior of this seesaw is controlled by the solution to that local minimum problem we just discussed. If HFGF has a local minimum at the origin, think of that as the center of our seesaw.
Got it.
The gadget tilts, creating a non-zero gradient.
So no stationary point then.
But if HFGF doesn't have a local minimum at the origin, the seesaw remains perfectly balanced, creating a stationary point.
Exactly. They've linked the two problems together.
They've ingeniously linked the existence of a stationary point for this new function, built using their seesaw gadget, to the existence of a local minimum for that earlier function, HFGF. And since finding that local minimum is hard, finding the stationary point must also be hard.
It follows logically.
Precisely. They've elegantly translated the difficulty from one problem to another.
It's a beautiful reduction.
The specifics of how they construct this seesaw gadget are laid out in the paper.
You can check it out.
But the core idea is this beautiful connection between the two problems.
That's the heart of it.
I'm really appreciating the depth and sophistication of their approach.
Yeah, it's impressive work.
They're not just throwing around terms like NP hard.
No, they're not.
They're backing it up with concrete mathematical constructions and rigorous proofs.
Solid mathematics.
Absolutely.
Yeah.
And this attention to detail is what sets this paper apart.
It's a high-quality paper.
It's not just about showcasing the challenges. It's about providing a solid mathematical foundation for further research in this area.
It lays the groundwork for future discoveries.
Okay, so we've established that finding these stationary points, even in an approximate sense, is computationally challenging.
It's a tough problem.
But mathematicians love a good challenge.
We do.
So are there any glimmers of hope? Any strategies for making progress despite these difficulties?
That's where things get even more interesting. The authors don't leave us stranded in a computational desert.
Okay, good.
They introduce a technique called the subdifferential sum rule relaxation, or SRR, as a potential path forward.
Okay, so before we jump into the SRR, let's make sure everyone's on the same page.
Good idea.
Can you remind us what a subdifferential is, especially in the context of PA functions?
Of course.
Okay.
So remember that PA functions with their sharp corners aren't differentiable in the classical sense. We can't always find a unique tangent line at every point. Right.
The subdifferential, in a nutshell, is a generalization of the derivative that captures the local behavior of a function.
Okay.
Even at those non-differentiable points.
So instead of a single tangent line, we might have a set of possible slopes that capture the function's behavior around those sharp corners.
Exactly.
Okay.
And for convex functions, this subdifferential is always a convex set, often taking the form of a polytope, a geometric object with flat faces.
Got it.
Now, the SRR technique tries to exploit this structure when dealing with PA functions, which, as we've discussed, can be expressed as the difference of two convex functions.
So we're leveraging the fact that even though PA functions themselves can be quite jagged, they're built from these nicely behaved convex components.
Exactly.
Okay.
Now, the standard subdifferential sum rule, which tells us how to find the subdifferential of a sum of functions, doesn't always hold perfectly when we have those non-convex differences.
So we can't just blindly apply the rule and hope for the best. Not always, no.
Right, but the authors give us a glimmer of hope with Theorem 4.11.
They do.
They introduce a precise condition called compatibility.
Compatibility, yes.
That tells us exactly when we can safely use a simplified version of the sum rule for those difference of convex PA functions.
It's a valuable tool.
Compatibility, it sounds like a key to unlocking a hidden door. But what exactly does this compatibility entail?
Think of it this way.
Okay.
The subdifferential of each of those convex functions at a given point is a convex set, often visualized as a polytope.
Oh.
The compatibility condition essentially says that if these polytopes align in a specific way,
Okay.
if they fit together nicely, then we're in good shape. We can use that simplified sum rule and analyze the function's behavior more easily.
So it's like saying, if the building blocks have compatible shapes, we can use a simpler tool to analyze the overall structure.
Perfect analogy.
And while checking for compatibility can be computationally challenging,
It can.
it provides a fundamental understanding of why certain approaches work and others fail.
It gives us insights.
It's like having a blueprint for success. We know exactly what conditions need to be met to overcome those computational obstacles.
It's a roadmap.
Indeed.
Now, while this theoretical framework provides a solid foundation, real-world computations are often messy and imprecise.
Right.
We rarely hit those approximate stationary points with perfect accuracy.
Right. Algorithms have to deal with finite precision and the inherent limitations of iterative processes. We need some wiggle room, some tolerance for those imperfections.
Maybe some flexibility.
Exactly. And that's where the concept of near-approximate stationarity, or ANUS, enters the picture.
Interesting.
It acknowledges that we might not hit those approximate stationary points exactly, but we can aim to get within a certain acceptable distance.
Makes sense.
So instead of demanding perfect accuracy, we're saying it's okay if our solution is within a certain tolerance, as long as we can control that tolerance and ensure it doesn't compromise the overall quality of our solution.
Exactly.
Precisely. It's a pragmatic approach.
It is.
That reflects the realities of computational limitations.
Yeah.
And to handle this, the authors introduce a beautifully designed algorithm called the butterfly net.
The butterfly net, I like that name.
The butterfly net, the name itself, evokes images of gracefully capturing those elusive points.
It's a good visual.
Can you walk us through how this algorithm works?
Sure.
Go.
Imagine you have a point, and you want to know if it's opponens.
Okay.
Meaning, is it close enough to an approximate stationary point given those tolerance parameters opponens?
Okay.
The butterfly net systematically explores the function's behavior around that point.
So it's like casting a net to see if we catch anything interesting.
A good analogy.
Okay.
The algorithm first checks if the point is already within that acceptable distance from an approximate stationary point.
Okay.
If it is, we're done. We've found a near-approximate stationary point.
And if it's not, what happens then?
If the point isn't close enough, the butterfly net doesn't just give up. Instead, it provides valuable information.
What does it tell us?
It tells us that we're at least a certain distance away from any NAS point.
So it's like a compass.
Yeah.
Guiding our search and telling us how far off course we are.
Exactly.
Right.
This information is crucial for refining our search and directing our efforts toward regions where we're more likely to find the near-approximate stationary points.
That's quite ingenious. And this butterfly net isn't just a theoretical concept. It has some impressive practical guarantees, right?
You're absolutely right. Theorem 5.8 establishes a remarkable result.
Okay.
It states that for a sequence of points that converges to a true stationary point, the butterfly net will eventually confirm DNS in polynomial time.
Polynomial time. That's a big deal in the world of algorithms.
It is.
It means the algorithm's runtime scales reasonably with the problem size, making it practically feasible for larger and more complex PA functions.
Exactly. This efficiency stems from the algorithm's clever design.
Okay.
It carefully exploits the structure of PA functions and the properties of those tolerance parameters to achieve this impressive performance.
So we have this powerful theoretical framework based on compatibility.
Yeah.
And we have this efficient algorithm, butterfly net, that can handle the practical realities of finding near-approximate stationary points.
Indeed. These tools provide a solid foundation for further exploration in this area. The authors have not only highlighted the challenges, but also offered potential solutions and a roadmap for future research.
It's a reminder that even in the face of computational complexity, ingenuity and mathematical rigor can lead to elegant and practical solutions.
Absolutely.
Welcome back to our deep dive into testing approximate stationarity concepts for piecewise Affine functions.
Yeah, good to be back.
We've covered a lot of ground, exploring the computational challenges, delving into hardness proofs, and uncovering some clever strategies for tackling these complexities.
It's been a great discussion.
But before we wrap up, I'd love to, dig a little deeper into those hardness proofs.
Okay.
I know we touched upon the high-level ideas.
You did.
But for our mathematically inclined audience,
Yes. Great.
I think it would be insightful to explore some of the finer points of those reductions.
I agree. Let's do it.
So let's revisit that PAR101 MAGX1 problem,
Okay.
which was key to proving the co-NP hardness of finding a local minimum for a PA function.
Right.
And remember, this problem involves vectors with components restricted to max1, 0, or 1.
Mm-hmm.
And we're trying to find a combination that maximizes their total length
Right.
using the O1 norm.
The O1 norm. Yeah.
And the challenge lies in the fact that there could be an exponential number of ways to combine these vectors,
It's a combinatorial explosion.
making a brute force search computationally infeasible.
Exactly.
So how did the authors connect this problem to finding a local minimum for a PA function?
Well,
They constructed those two special functions, HF and GF, if I recall correctly.
you do.
So the construction of HF and GF
Yeah.
is where the true ingenuity lies.
It's quite clever.
Let's start with HF, which is essentially a scaled version of the norm.
Okay.
Remember, the your norm measures the maximum absolute value of a vector's components.
The largest one, yes.
So HF takes a vector,
Yeah.
finds a component with the largest absolute value,
Right.
and then scales it by some factor.
That's it.
Now, GF is a bit more intricate.
It is a bit more complex.
It's defined as the maximum of two terms.
Okay.
The first term is simply that same scaled norm
Same as HF.
we used for HF.
Right.
Second term is where things get interesting.
That's where the magic happens.
It incorporates those special vectors from the PAR101 MAGX1 problem.
Those vectors come into play.
Can you elaborate on how those vectors are incorporated into GF?
Sure.
Okay.
So the second term of GF involves calculating the inner product of the input vector with each of those special vectors from the PIR1, 0, 1, MAX1 problem.
Okay.
Now, the inner product, for those unfamiliar, is essentially a way to measure how much two vectors align with each other.
So GF is a combination of the norm and a measure of how much the input vector aligns with those special vectors.
You got it.
And here's the crucial insight.
Okay.
By carefully choosing that scaling factor,
Yes, R is important.
which determines how much we stretch or compress the inner norm,
Right.
the authors create a direct link between the solutions of the two problems.
It's a bridge.
So that scaling factor, R, acts as a bridge
Yes, a bridge between two worlds.
between the worlds of PAR1, 0, 1, MX1, and finding a local minimum for HFGF.
Exactly. Lemmas 3.1 and 3.13 in the paper formalize this connection. They demonstrate that if you can find a local minimum of HFGF, you can directly extract a solution to the PAR101 MXX1 problem.
So solving one problem gives you a solution to the other.
And vice versa.
And conversely,
Yeah.
if PAR1 MX1 has a solution with a certain length,
Right.
then HFGF must have a local minimum.
It's a two-way street. They're connected.
It's a beautifully crafted two-way street,
Yeah.
demonstrating that solving one problem essentially solves the other.
That's the beauty of it.
And since we know PAR101 MX1 is co-NP hard, this reduction argument firmly establishes the co-NP hardness
Yes.
of finding a local minimum for HFGF.
It's a solid argument.
Exactly. It showcases the power of reduction arguments
Are powerful tools.
in theoretical computer science.
Absolutely.
By linking problems together, we can transfer complexity results and gain a deeper understanding of the challenges we face.
It's about connecting the dots.
Okay, that was a brilliant deep dive into the local minimum case.
Yeah, we went deep.
But the general stationary point case, which involved that fascinating seesaw gadget, was even more intricate.
It was quite clever.
Can we unpack that a bit further as well?
Let's do it.
So, remember, the seesaw gadget
Yes.
is built from two convex PA functions, HC and GC, which are carefully designed to mimic the behavior
Right.
of a seesaw balancing at its center.
Like a perfect balance.
Right, and the tilting or balancing
Yeah.
of this metaphorical seesaw was directly linked to whether or not HFGF had a local minimum at the origin.
That was the key connection.
So if HFGF has a local minimum at the origin, the seesaw tilts,
it loses its balance.
meaning no stationary point for HCGC.
No stationary point.
But if HFGF doesn't have a local minimum at the origin,
Yeah.
The seesaw remains balanced,
Perfectly balanced.
corresponding to a stationary point for HCGC.
Exactly.
They've brilliantly translated the difficulty
Get the clever trick?
of finding a local minimum for HFGF into the difficulty of finding a stationary point for HCGC.
They've shifted the problem.
And since we know finding that local minimum for HGF is co-NP hard,
Right.
this implies that finding a stationary point for HCGC must be at least as hard,
At least as hard, if not harder.
pushing it into the realm of NP hard problems.
Into the realm of the truly difficult.
Exactly. Lemma 3.13 formally establishes this connection,
It's all there in the paper.
demonstrating the NP hardness of the general stationary point problem.
It's a tough nut to crack.
So these hardness proofs
Yeah.
are a testament to the author's deep
They
understanding
really understand this stuff.
of computational complexity
Uh-huh.
and their ingenuity in connecting seemingly disparate problems.
They've bridged the gap.
It's a reminder that even seemingly simple questions about PA functions can lead to profound computational challenges.
It's deeper than it looks.
But it's not all doom and gloom.
No, it's not.
The paper also presented some promising avenues for making progress,
Like what?
like the subdifferential sum rule relaxation
SRR. Yeah.
and the butterfly net algorithm.
Those are powerful tools.
Absolutely. The SRR offers a potential way to simplify the analysis by exploiting the fact that PA functions
Yeah.
can be expressed as the difference of two convex functions.
It's a clever decomposition.
And the butterfly net provides an efficient way to handle the practical realities of finding near-approximate stationary points.
It's a practical solution.
It's a great example of how theoretical insights
Yeah.
can guide the development of practical algorithms.
Theory and practice working together.
So this paper has been a fascinating exploration
It has.
of the interplay between optimization, geometry, and computational complexity.
A beautiful intersection of ideas.
It's been a deep dive into the world of piecewise affine functions, revealing both the beauty and the challenges of these ubiquitous mathematical objects.
They're everywhere.
And it serves as a reminder
Yeah.
that the quest for efficient algorithms and deeper mathematical understanding is an ongoing and rewarding endeavor.
It's a journey worth taking.
Thank you for joining us on this intellectual adventure.
It's been a pleasure.
We'll be back soon with another deep dive
Looking forward to it.
into the fascinating world of mathematical research.
Keep exploring.
Until then, keep exploring, keep questioning,
And keep pushing those boundaries.
and keep pushing the boundaries of knowledge. Welcome to the Deep Dive. Today, we're going to be taking a deep dive into some really fascinating mathematics. We've got a paper here titled Testing Approximate Stationarity Concepts for Piecewise Affine Functions, dated January 7, 2025. And, I think we can just jump right into it.
Yeah, definitely. This paper really dives right into the problem of efficiently finding near stationary points in these piecewise affine functions. And as you know, these functions are really important in a variety of machine learning applications. And as you know, these functions are essentially glued together from straight lines or planes, creating those characteristic sharp edges.
Yeah, and even something like a basic test for stationarity, like checking if the gradient is close to zero. It's surprisingly tricky with these piecewise affine functions.
Yeah, the paper mentions that it's actually NP hard for piecewise affine functions, meaning that as the problem size grows, the computational time just explodes, making it practically impossible to solve.
Yeah, it's like hitting a wall. So how do we even begin to approach this? It seems like they start by exploring ways to represent these piecewise affine functions.
Exactly. So they focus on two main representations. The first one is called the DC form, which expresses the function as the difference of two convex functions, kind of like taking two smooth bowl-shaped functions and subtracting one from the other to create those sharp edges.
It's like sculpting a complex shape by carving it out from a smoother block.
Yeah, that's a great analogy. The second representation is the max-min form. Here, the function is represented as the maximum of a set of minimums of any functions.
So it's like finding the highest points on a landscape made up of valleys.
Precisely. Now, the authors show that even with these representations, figuring out if a point is truly a stationary point, not just approximately, is still really computationally hard.
So where do we go from here?
Well, this is where they introduce this really clever concept called relaxation. It's like a way of simplifying the problem to make it more computationally feasible. And they do this by using the subdifferential, which is kind of like a generalization of the idea of a derivative for functions that aren't always smooth, like our piecewise affine functions.
So it's like smoothing out those sharp edges a bit.
Exactly. And to work with these subdifferentials, they use the subdifferential sum rule, which helps to calculate the subdifferential of a function. That's the difference of two other functions. But here's the thing. This rule doesn't always work perfectly for non-convex functions.
So there are still some limitations.
Right. And to address this, they introduce a new condition called compatibility, which tells us when the subdifferential sum rule will actually work for those non-convex functions. And what's really cool is they connect this to geometry. They show that these subdifferentials at a point are compatible if these corresponding polytopes have this very specific geometric relationship.
This is getting really interesting. Now we're linking mathematical concepts to tangible geometric shapes. Could you elaborate a little bit more on this connection between subdifferentials and polytopes? What's going on there?
Yeah, so essentially they show that checking for this compatibility is equivalent to checking if the subdifferential sum rule applies. They formally lay this out in Theorem 4.1. They state that for convex piecewise affine functions h and g for any point x, the subdifferential of the difference function at x denoted x is equal to the difference of the individual subdifferentials, if and only if the polytopes are compatible.
So it's like having a two-way street between the world of subdifferentials and the world of polytope geometry. This compatibility condition seems really crucial, but didn't you mention that checking it directly can also be computationally expensive?
You're absolutely right. And that is precisely why they introduce another condition called transversality, which is much easier to check and guarantees compatibility. It's sort of a shortcut to making sure those subdifferentials play nicely together.
It's like having a quick test to make sure everything's going to work as expected.
Yeah.
Could you elaborate on this transversality condition a little bit? How does it relate to the subdifferentials?
Okay, so imagine that you shift the subdifferentials by some vectors. Now, if these shifted subdifferentials only intersect at the origin, then we say that the functions are transversal at that point. This is what they define in definition 4.2. If x and intersect only at the origin, then functions h and g are transversal at point x. They show that this is the same as saying that the intersection of specific sets pari x only contains the zero vector.
Okay. Can you break down what par means here? I don't think I use that one every day.
Sure. So pari x represents the subspace parallel to the affine hull of the subdifferential of h at the point x. It essentially captures the direction of the set xx.
Ah, okay. So this transversality is all about ensuring these subdifferentials don't overlap in their direction.
That's a great way to put it. And the nice thing is that they show you can check for transversality very efficiently. For functions in what they call NMC form, there's an algorithm that can check for transversality in polynomial-time.
Okay, so we have a condition that guarantees compatibility, which ensures our subdifferential sum rule works, and it's computationally efficient to check. This seems like a really powerful tool. But how does all this theoretical stuff translate to the real world, particularly in machine learning? That's what I'm most interested in.
Well, you're in luck. The authors don't leave us hanging. They show how this theoretical framework can be applied to a number of different machine learning problems. They talk about its use in SVM with a specific loss function that's good at handling outliers, continuous piecewise, affine regression, and even analyzing real U neural networks.
Okay, that's really cool. But before we jump into those specific applications,
Yeah.
I'd like to pause for a second and just take a closer look at how they address this issue of rounding and finite termination. You know, in the real world, we often can't find those exact non-differentiable points because of the limitations of computers and the randomness in a lot of our algorithms. How do they handle that?
Yeah, that's a great point, and they definitely address that. They acknowledge that in practice, you're not going to have that absolute precision. So they develop an algorithm that checks for something called DALANE, near-approximate stationarity, which is sometimes shortened to NAS.
So they're basically aiming for solutions that are good enough rather than perfect.
Yeah.
Which, you know, in the real world is often what we have to do.
Yeah.
Can you talk a little bit more about this ANAS concept?
Sure. It's essentially a way to figure out how close a point is to being truly stationary while taking into account things like finite precision and the randomness of algorithms. The A represents the tolerance we're okay with in terms of the function value, and the R represents the probability of making a mistake in our determination.
So we're essentially setting a threshold for close enough.
Exactly. And as part of their algorithm, they developed this really clever oracle.
An oracle. That sounds intriguing. What exactly does this oracle do?
Think of it like a powerful tool that can tell us, for a given point and a specific tolerance, whether or not that point is stationary. We use this oracle to navigate the search space and see if a point is potentially a near-approximate stationary point.
I like this oracle idea. It simplifies things a lot. But doesn't relying on an oracle create its own computational problems? Especially since we are already dealing with NP hard problems.
You raise a valid point, and the authors definitely acknowledge that even with a really good oracle just detecting NAC is still a tricky problem for piecewise affine functions from an information theoretic perspective. So they introduce this thing called a separation function.
So it's like defining what close enough actually means in a mathematical sense.
You got it. They define this constant r, which captures the maximum steepness of the function, essentially the largest possible jump. And then they define these functions, O sub j sub w, which measure the gaps in function values between different pieces of our piecewise affine function. And then they combine these with r to define the separation function, sub w. And this function basically tells us, for any point, how far we need to move to be confident we're near a true stationary point.
Okay, so they've taken this abstract idea and given it a solid mathematical definition. I'm really impressed by how they've woven all these complex ideas together, but we're still missing a piece of the puzzle, right? We still need the algorithm itself. How do they actually use this separation function to detect those NAS points?
That's where their brilliant creation comes in. The butterfly net algorithm. They use this algorithm in conjunction with the separation function and the oracle to create a really robust way to find these near-approximate stationary points. But I think to really understand the specifics of the algorithm and how they prove it actually works, it might be a good place to pause, and then we can pick up in the next part of the deep dive.
Yeah, I agree. This butterfly net algorithm sounds like a game changer, and I definitely want to understand how it works. So let's take a quick break and come back to figure out the rest.
Welcome back. Before the break, we were about to dive into the butterfly net algorithm, which is the author's solution to finding those NAS points.
Right. I'm excited to hear about it. This algorithm sounds like it's doing something pretty amazing. How does it actually work?
Okay, so the algorithm starts by defining these nested sets. Each set represents a level of precision, so you can kind of think of it like zooming in on a map. Each set is like a more refined area of our search space.
Okay, so I'm visualizing those nested sets. What's the idea behind them? Why not just search the whole space all at once?
Efficiency. By narrowing the search space this way, the algorithm doesn't waste time on unnecessary calculations. And to do this, they cleverly use that separation function we talked about earlier. They start with a set called sup, which contains all the points that could potentially be stationary. So that's kind of our starting point, our widest net.
So sup is like a first filter, capturing anything that even remotely looks like a stationary point.
Exactly. Then they use the separation function to define a bunch of smaller sets, each one based on a specific radius determined by the separation function. Remember, the separation function tells us how close we need to be to a true stationary point to be confident we're within that tolerance. These smaller sets are called supy sub, and they're like finer nets capturing only points close enough to be considered those near-approximate stationary points.
So it's like a series of concentric circles closing in on those stationary points.
Yeah, perfect analogy. But they don't stop there. They also create another set of sets called a supy sub, which are designed to exclude points that we know are not knots.
So it's like a double filter, catching the good stuff and getting rid of the bad stuff.
Exactly. And here's the best part. The algorithm checks these sets really efficiently using an oracle. If a point is inside supy sub, but outside a supy sub, the algorithm calls on this oracle to tell us if it's truly a near-approximate stationary point.
It's amazing how they've connected all these abstract mathematical ideas, you know, the separation function, these sets, and then this oracle, to create this algorithm.
Yeah.
But how do we know it actually works? How do they prove that?
They actually have a very rigorous proof showing that this algorithm either finds a true near-approximate stationary point within our tolerance, or it correctly tells us that there's no such point within a specific radius. The key to this proof is lemma 5.3, which states that for any piecewise affine function, if the algorithm outputs a point x, then with probability at least 1, x is an iterative point of f.
Okay, so they're not just saying it works, they're actually backing it up with solid math. Can you walk us through the main steps of the proof? What are the key things that make it work?
Yeah, so the proof is really interesting. It uses both geometric intuition and some really careful mathematical arguments. They leverage the properties of the separation function and those special sets we talked about, the super-sub-sub and a super-sub-sub-sub. They show that if a point is inside super-sub-sub-sub, but outside auspicious-sub-sub-sub, and the oracle says it's stationary, then it has to be a NAS point with a very high probability. On the other hand, if the algorithm stops without finding such a point, it means that no such point exists within the area we've explored, and that area is determined by the separation function.
Wow, it's really impressive how much care they put into this proof.
And then they even go further and show that this butterfly net algorithm runs in polynomial time, at least for functions with a certain structure. This is in theorem 5.4. So this means that for those functions, the algorithm doesn't get too slow as the problem gets bigger.
That's really important. It means we can actually use this algorithm in practice.
Exactly. It's all about combining theory with practicality. And to show us how it works in action, they actually apply the butterfly net algorithm to a very specific problem, testing for ANAS in convex piecewise affine functions. And they start with a really simple example in just one dimension, just to make it easier to understand.
Oh, that's always helpful. Starting simple is a good way to learn the basics. How do they set up this one-dimensional example?
So they imagine a function that's made up of a bunch of linear pieces, each with a different slope. Then they show how to use the butterfly net algorithm to find a point that's stationary for this function. And then they point out that if you have a good algorithm for finding a stationary point for a convex piecewise linear function in one dimension, you can actually use that same algorithm to find a point for any convex piecewise affine function. And the running time is still polynomial in the number of pieces.
Okay, I can picture that. But things must get a lot more complicated when we go beyond one dimension, right? How do they handle that?
Well, they generalize this one-dimensional approach by building a net in higher dimensions. This net is basically a set of carefully chosen points that kind of represent the function's behavior in that higher dimensional space. They use the idea of hyperplanes and the properties of convexity to create a net that really captures what the function is doing.
So it's like placing sensors strategically to understand a complex landscape.
Exactly. And the algorithm searches this net, throws out any points that are obviously not near-approximate stationary points, and then uses the oracle to check the remaining candidates.
This is a really elegant solution.
Yeah.
But do they show how it could be used beyond just convex functions? A lot of real-world problems involve functions that are more complex than that.
They do. They actually extend their results to a bigger class of functions called NMC functions. These are functions that can be written as a combination of convex and affine functions. And they show that the butterfly net algorithm still works for these functions, even though they might not be convex.
Wow, so it's even more versatile than we thought.
Exactly. And they give a detailed proof for this more general setting. And to wrap up the discussion of this algorithm, they make a really important point. This butterfly net algorithm isn't tied to just one specific definition of stationarity. You can actually use it with different kinds of generalized subdifferentials like the Frechet and limiting subdifferentials.
That's awesome. It's like having a multi-tool that you can adapt to different situations.
Exactly. As long as we have an efficient oracle for checking whatever stationarity concept we're using, we can plug it into this algorithm and find near-approximate stationary points really efficiently. But let's not forget why we're doing all this. What kind of applications do they show us? They give us some really interesting examples of how this works in practice. One example they talk about is support vector machines, or SVM for short, specifically with the margin loss.
I've heard of SVM, but the margin loss is new to me. Can you give me a quick explanation of what that is and how it connects to what we've been talking about?
Of course. So SVM is a method used in machine learning to classify data. It's all about separating data points into different categories. The margin loss is a special type of loss function used in SVM. It's designed to be more robust to outliers, which are those data points that don't really fit the pattern.
So it's like a more forgiving classifier that can handle some noise in the data. How does this relate to the piecewise affine stuff and the stationarity tests?
They show that you can actually write the objective function of SVM with the margin loss as a piecewise affine function. And this is really important because it means we can use all the tools we've been talking about, like the butterfly net algorithm, to understand and solve these SVM problems. They specifically state that the margin SVM problem is the same as finding a Clark stationary point of a particular piecewise affine function, and then they note that we can use the butterfly net algorithm to find a near-approximate stationary point for this problem.
So they're showing us that these tools they've developed can be used in real-world machine learning applications. That's pretty cool.
And they don't stop there. They also talk about continuous piecewise affine regression. This is like fitting a model to data, but instead of using a smooth curve, we use a series of straight lines that are connected together.
So it's like a more flexible way to capture the trends in the data.
Right. And again, they show that you can write the objective function for this type of regression as a piecewise affine function, which means we can use their methods to analyze it. Specifically, they say that if the loss function is the Huber loss, then this can be solved using the butterfly net algorithm, which can efficiently find a near-approximate stationary point.
I'm starting to see how widely applicable their work is.
They also talk about neural networks, specifically the ones that use ReLU activation functions. ReLU stands for Rectified Linear Unit, and it's really popular in deep learning. And they show that even though ReLU isn't smooth, you can still use their methods to analyze the stationarity of these networks. They start off by discussing a specific activation function called the leaky ReLU activation function. They say if this is the activation function being used, then the objective function of the network is a piecewise affine function, which means they can apply their techniques.
That's really fascinating how they're connecting all these different areas. But how do they deal with the fact that neural networks can be so complex with so many layers and parameters?
They start simple. They begin with networks that have just one hidden layer, and then they work their way up to more complex architectures. And they show us how to write the objective function for these networks as a piecewise affine function so that they can use their framework.
I'm following their approach. But even a network with one hidden layer can have lots of parameters. Doesn't that make things computationally difficult?
It does, but they have a really clever way to deal with that. They focus on what they call essentially active indices. It's a way to reduce the number of parameters we have to think about. Specifically, they say that for neural networks with one hidden layer, if the activation function is piecewise affine, then they can rewrite the stationarity conditions in terms of these essentially active indices. And this makes checking for stationarity easier because we don't have to look at all the indices, just a smaller subset.
Essentially active indices. It sounds like they're figuring out which parameters are the most important for analyzing stationarity.
That's a great way to put it. It makes their approach much more efficient. But even with all these simplifications, they show that it's still really hard to figure out if a point is stationary for a ReLU neural network. In fact, they prove that the problem is still NP-hard.
Oh no, that computational wall again.
Yeah, it seems like it always comes back to that. But it's important to remember that this doesn't mean we should give up. It just highlights how complex these neural networks are and why we need these advanced algorithms, like the butterfly net algorithm, to help us find solutions.
Welcome back. We've been on quite a journey exploring these piecewise affine functions, their stationarity, and their role in machine learning. I'm really curious to see what kind of open questions this paper leaves us with.
Yeah, the authors definitely point out some areas where there's still a lot more work to be done. One thing they mention is that their main focus was on these piecewise affine functions, which are just one type of function. So a natural question is whether their techniques could be extended to handle more general, piecewise smooth functions.
Yeah, that makes sense. Expanding their framework to include a wider range of functions would make it even more useful for machine learning. What other open questions did they bring up?
Well, they also talked about the need for more efficient algorithms for actually finding these near-approximate stationary points, especially when we're dealing with high-dimensional problems. You know, a lot of their work focused on the difficulty of just testing for stationarity, but it's one thing to know these points exist, and it's another to actually find them quickly.
It's like knowing there's treasure buried somewhere, but needing a better map to actually locate it.
Exactly. And they also highlighted the need for more research into how these techniques can be applied to specific machine learning models, looking at more complicated neural networks, different activation functions, things like that. There's a lot of potential there.
It sounds like they've given us a roadmap for a ton of future research in machine learning. Before we wrap up, though, I'd like to go back to one of their applications that we talked about earlier, the one about using their framework to train penalized deep neural networks with stochastic gradient descent. It seemed like a really good example of how their mathematical ideas can actually be used in practice.
Yeah, that's a great example. It shows how these abstract concepts can have a real impact on machine learning. As we mentioned before, stochastic gradient descent, or SGD, is a common algorithm for training these networks. It's like taking small steps down a hill, always trying to go in the direction of the steepest descent to reach the lowest point.
Right, but the stochastic part means we're not always going in the exact right direction because we're only using a small sample of data at each step. So how do we know when to stop? How do we know when we're close enough to a good solution?
That's where the butterfly net algorithm really shines. They use it as part of a new algorithm for training penalized deep neural networks with SGD. It essentially gives the algorithm a way to sense when it's close enough to a good solution, even though we're working with limited information.
So the butterfly net algorithm acts like a guide, telling us when we're close enough to the bottom of that valley.
Precisely. And what's really impressive is that they were able to prove that this new training algorithm will actually converge to a point that's near a true stationary point, even for deep neural networks that have lots of parameters, which can be very complex.
Wow, that's a big deal. So they didn't just have a good idea, they actually proved that it works mathematically.
Yeah.
Did they also do any experiments to test it out?
Oh, yeah, absolutely. They did a bunch of experiments with real-world data sets, and they found that their algorithm works just as well as other methods out there, but with the added benefit of having these strong theoretical guarantees.
This is a perfect example of how theory and practice can come together. They took a complex mathematical idea and turned it into something that can actually be used by people working on machine learning.
I agree. It just goes to show you how powerful mathematical thinking can be. It helps us to understand the world, and it also gives us the tools to build new things.
This has been a truly incredible deep dive. We've gone from these very abstract concepts to some really cutting-edge applications of machine learning.
It's been an amazing journey, and as the authors have shown us, there's still so much more to discover. This paper is really just the start of a whole new way of thinking about stationarity and what it means for machine learning.
I think our listeners will agree. This has been a really thought-provoking look at how we can use math to solve real-world problems.
Absolutely. And I encourage everyone to keep exploring these ideas, to think about those open questions that the authors raised, and to keep pushing the boundaries of this field.
And on that note, I think it's time to wrap up this deep dive. A huge thank you to our expert for guiding us through all of this.
It was my pleasure. And to our listeners, keep that curiosity alive, keep exploring, and never underestimate the power of math. Until next time on The Deep Dive.